Okay, so we're going to start with a question on chapter 13.
Yeah.
Chapter 13, section C, using Eno's data set, comparing the impossible to the other conditions as far as the post-quiz heart rate.
Yes. So it says to use the code chunk from the tutorial before. So
oh, the tutorials got deleted out of there, so no, that won't help you.
Okay. I was wondering about that. Well, but it was, so the same code chunk I just found up above. And
okay, so there's a little bit different. So instead of impossible, you have to put the name of the variable there. And so that's the EXP underscore COND. Is that the name of it? Experimental condition?
Okay. So that's what was in there before, like,
yeah.
Let me see. Not that one.
You need an underscore too between EXP and COND.
And then,
okay, yeah. Sorry. Go back.
Yeah, so EXP and then the underscore.
Okay.
So now if you run those two lines, but not the pipe at the end of the second line, not the pipe at the end of the second line.
Yeah.
No, the whole thing. So that gives you all the pairwise tests. We don't
just run
pairwise on this one. Well, let's see. Yeah, that's Fisher's LSD looking at all pairwise. Okay.
Okay, wait, sorry. I think it was, no, these are the ones that were already in place for us. And then it's the C1.
Okay.
Is that right, Leah?
Yes.
Yeah, that's right. Yeah, it's the contrast statement.
Okay,
yes.
So take off the pairs at the end, because that's for pairwise. And we're not going to do pairwise. So take off line 160.
Okay.
And take off the pipe at the end of the next line for now. Run that. So we're running just the EM means, and we see the order. There are how many groups? How many levels to the factor experimental condition? There's 4. Where is impossible in the order?
The bottom.
It's the last. It's the 4th. So we're going to compare the top 3 to the last one, the 4th one. So that matters, that order matters when we're going to do our weights. So how are we going to do our weights if we have the 1st, 2nd, and 3rd together compared to the 4th? What's one way we could do our weights?
Could you do like -1, -1, -1, and then +3?
That is totally cool. So let's do that. So put a pipe at the end of this line.
Okay.
And then it's EM means double colon contrasts. Contrast singular. And
contrast.
And then after you say contrast, you open parentheses. Now you have to say list and then open another set of parentheses. Now you're going to put some quoted text to remind you what you're doing. So you could say impossible versus the rest. And this is just text for you. And you want to keep it kind of short so it doesn't like run on to the page. Okay, so after you have this quoted text, make it equal to, and then a concatenate a letter C, and then parentheses. Mush the C to the parentheses.
Oh,
so no space there. Yep. And now this is where you're going to put your weights. And you said -1, comma, -1, comma, -1, comma, 3. Now run that.
Okay. Awesome.
Thank you.
Rates. You could have +1, +1, +1. Then you'd need a -3.
So what is the label of impossible first rest? That's just a label for me to know?
Text that you have entered to remind yourself what it is.
Okay. Okay. And so the last one, I guess I'm just trying to figure out still like.
Can you go up to the plot?
Yeah.
So stop there. So look at this plot. So can you shrink down the bottom part of your screen?
Oh, yeah.
That tab.
Ah.
Yeah, if you pull that down, it's a little easier to see. So we've got the easy, moderate, difficult, and impossible. So we just merged easy, moderate, difficult, those first 3, and compared it to impossible. Is there another way that you think would do a better job of making a cleaner distinction? Another way to lump those groups?
Maybe between easy, moderate, and difficult, impossible.
Yeah, if you lumped easy, moderate, and compared it to difficult, impossible.
Oh,
Yeah, and if you were going to do that, Melissa, what weights would you choose for that, to do that one?
You could do like +1, +1, -1, -1.
There's one set of weights you could use to do that.
okay. So it's just that whenever you're comparing like or contrasting, you want to put all the weights that you're comparing on one side in negative and all the weights on the other side positive, and they have to add up to each other.
Yes. So
Okay.
groups that you lump together have to have the same weight as each other. And all together it has to be 0. And to do that, you make one lump have a positive number and the other lump have a negative number.
Okay. Got it. Okay. Thank you.
That was a good
Thank you,
question.
Sarah.
Yes. Anyone else have any questions on this one? No? Okay. All right. Well, are we ready to move into two-way ANOVAs now? We've done one ways. Now we're going to go to two ways. Let's get my mouse over here. Okay. So you can stop sharing your screen. Thanks, Laura. That was so great. So I'm going to share my screen now. Shared that screen. And here we go. Let's bring up. So I wanted to show you, look at this list of chapters. Where are we? We're almost at the end. So today we're going to do the two-way ANOVAs. And there's a PowerPoint right here that we're going to go through. But there is also another PowerPoint right up at the top that's kind of by itself. This is the example that Cohen goes through in the book of the two-way with interaction, two-way ANOVA with an interaction contrast. And we'll go over that one as well. I wanted to show you on our YouTube channel. So this is the YouTube channel. If you go to the playlists, there's a playlist called Out of Class Lectures. Chapter 13 on multiple comparisons. I have last semester's lecture recordings, and I have chapter 14, the example PowerPoint, and then the chapter PowerPoint, both recorded here, as well as chapter 15. Now, when I did chapter 15, first I did a half hour on how to use R, and then I did the class, but we had to pause it, and so it ends up, they're two separate ones, but together it's an hour-and-a-half lecture. Chapter 16, there is 2 classes recorded. Those are there from before. And again, this is in the out-of-class lecture playlist on the YouTube channel.
Can I put my plug in that I loved that? That seriously saved my life to watch the chapter 14 ones to help me understand the reading. Just FYI, found these, saved me yesterday from swearing a lot.
If I had realized, I forgot. I mean, I knew that they were up there, but I forgot. But I wish I had told you guys to watch those before, but I didn't realize today. I was like, oh yeah, they're there. I already had them there. But they're there now. At least you can use them. In in the assignments in Canvas, chapter 14 is ready to go. If you find any where you're not getting the right answer and you're like, I think I did it right, email me. They have been used, so the answer should have been checked, but always check with me if you can't get the right answer, because it could be an error on a setting in Canvas. So we want to make sure that, email me. Don't bang your head against the wall. Okay, I think, I did find this. So I put up here this link on our homepage. This is the PDF that has a lot of, where did it go? Just clicked it. Yeah, there, it's gonna open it again. So this is the APA guidelines for reporting examples and tables. There is also now this second link. This is for the JARS, which stands for Journal Article Reporting Standards. So this is by APA, the APA. So this is the source. So this is the link that goes to the quantitative methods. There is links at the bottom for the qualitative and mixed methods papers. They have slightly different standards, but it has lots of information for you. So general reporting this is like 3-page high points. So what should be on your title page? What should be in the author notes? So your introduction, your methods section. In the methods sections, we talk about inclusion and exclusion criteria. What are my participant characteristics? How did I sample them? What's my sample size? Did you do a power analysis beforehand? What are your measurements and covariates? How did you collect your data? What's the quality of your measurements? What instruments did you use? Were you masked and blind? Is there any psychometrics that you have on the scales you chose? Tell us about the conditions and the design of your experiment. What data diagnostics did you run? And what's your analysis strategy? So this has been what we focus, when I've had you focus on writing these up, we kind of do a little blip of all that stuff, but the analysis strategy, what are you going to, what's your research question? What method are you going to do a one-way ANOVA to test if the 3 different majors have different heart rates? And then the results section. Usually we have a participant flow diagram if we've lost participants, or at least talk about that. And then the statistics and data analysis. There's a whole bunch of stuff here to help, this is kind of like a bullet list of things you should include when you're writing up your statistics and data analysis. This isn't like a perfect thing to follow for class, but this is I thought would be helpful for you as you write things in the future. And so things like including, is there missing data? If so, how do you address it? Descriptive statistics. Now, when you go to inferential statistics or anything that has a p-value. So inference is when you take a sample and you make an inference or a statement generalized about the whole population. So any of these hypothesis tests that get a p-values, those are inference. So in this NHST, that's null hypothesis significance testing, that's all that we're learning about, t-tests and ANOVAs. What method do you use? You need to give degrees of freedom, mean squared error. So they're saying, yes, include the mean squared error. Always include effect sizes and confidence intervals, not just a p-value. And clearly say if you're doing one-sided, two-sided, what you're looking for. So I thought this would be nice for you guys to have a link to as you are becoming writers of this kind of stuff. So I talked to Sean Whiteman, our interim associate dean for research, about putting together some kind of packet or resources on this kind of thing for us to put together. So hopefully we'll get something worked out for future, because this is something I think there's little bits everywhere, but there's not like one source of this information. Okay. All right. Let's quickly start with that slideshow that was linked at the top of the table on our website. So on the website, it's this PowerPoint example, chapter 14, two-way ANOVA with interaction contrast. I'm going to start with that one. And this is the example that is in your book. So we should have all read that. So we'll see how this goes. Okay. So far we've seen one-way ANOVAs. So the primary thing that we've learned from the one-way ANOVAs, independent groups ANOVA, is they're like the independent groups t-test, but we are allowed to have more than 2 groups, bonus. With a two-way ANOVA, the bonus thing here is we get to have 2 factors to break our sample up. We're still gonna have a dependent variable. Your dependent variable is your continuous interval ratio-ish scale that you're comparing the averages of. The example in the book talked about think it's a made-up study, looking at scores on a video game that simulated driving a large truck at night. And they wanted to know how different factors affected people's ability to have reaction times and to drive well late at night. And they had not one, but two factors they wanted to investigate at the same time. Now, we could have done these factors one at a time with a one-way ANOVA, but hopefully by the end of today, you'll see the benefit in doing a two-way ANOVA. So the first factor or independent categorical variable they wanted to investigate was how much sleep had an effect on this driving score, how many errors they made driving on this simulation. So they randomly assigned all the subjects to one of 4 sleep conditions. Now see which one you would want to be in. Control group, sleep whatever you want. Jet lag, they only let you sleep after 11 p.m. or not after 11 p.m. to 7 a.m., but as much as you wanted. Interrupted, you could only sleep 2 hours at a time and then they kept you awake for an hour. Or total sleep deprivation. So these people were kept in a sleep lab for 4 days and had whatever they were assigned to, that's the sleep they got for 4 days or did not get. This is made up data, I think. So that's great, but also at the same time, they wanted to investigate the effect of a stimulant. They're calling it the stimulant condition. People were randomized to either get caffeine pills or a sugar placebo. They weren't told which was which. Or, how would you like this? The reward category. They were told that they would get money for good performance, but if they did poorly, they got electric shocks. Yeah, how would you like to be in group 4 of the sleep and 3 of the stimulant? You know, this is fun stuff, right? So they are looking at, in this situation, in this research, 2 different factors. Now, each subject is in one sleep condition and one stimulus condition. So they're in one of each of those. So how many combinations are there? 4 sleep, 3 stimulant. 12 total combinations. 3 times 4 is 12 combinations. So before, when we did one-way ANOVA, we talked about K was the number of groups. Now, when we do a two-way, we don't say K is 12, although there are 12 different combinations. What we talk about is it's a 4 by 3, that we have 4 levels of the first factor and 3 levels of the second factor, but 3 times 4 is 12. In this scenario, we have 5 subjects for every one of those 12 combinations. So that's a total sample size of 60. So here's the data, and I've entered them in R, so I'm showing the syntax for entering these in R, and I use the gather syntax here. I need to update it to the pivot longer, but here is the data that's shown in your book. So each of the 4 sleep conditions are a row across the table, and each of those stimulant conditions are each of those 3 columns. So there are 12 combinations or 12 cells. And in each combination or cell, there is 5 participants. So there are 5 white scores, 1 for each person in that combination. So in the people that had normal sleep and the sugar pill, their scores were 24, 20, 29, 20, 28. In the electric shock dollar bill, total lack of sleep, their scores, those 5 people were 15, 11, 19, 11, and 17. So higher number means you did better, lower number means you did worse. So this is the score on the video game. Well, stimulation game. So here it is in R. The way the data is arranged here is very concise and takes up little room in a textbook. But is this first 24 connected to this first 26 and this first 28? They're not. These are 5 different people. Each group is totally independent of the other group. So when we enter this, we need to have one, in our R, we need to have 1 line per person. And then when we do this gather command or the pivot longer, we end up with 1 line per person. So we have a variable called sleep, which says what kind of sleep situation they were in, stimulant, which says what stimulant situation they were assigned to, and then the last variable is their score, and it's their driving score. So now we have 60 lines in our data set, 1 line per person, and these 3 variables. So that's how we would want it in our computer program, 1 line per person. But we're going to look at this table with all the numbers together in a more condensed way as we move forward. So to get kind of started on any problem, what do we always want to do first before we do any kind of statsy stuff? We always want to do exploratory data analysis. We want to summarize and we want to plot. Always summarize and plot before you do anything else, because it will help you understand your data 1 at a time, 1 variable at a time, and 2 variables at a time, and it will help set you up to where you can understand your model. It'll also key in if there's any mistakes or anything interesting you need to take a look at. So up here at the top, I've started with the name of my data set. I've grouped by sleep, that's one of my variables, and I did furniture table 1 of my scores. That will give me descriptives for each sleep group. So if we look at those averages, are those what you would expect of the averages? The own schedule, average score was 25. Jet lag, average score was 24. Interrupted sleep, average score is 18. Total lack of sleep, average score is 16. Would you expect that? Does that seem reasonable? Okay. This is called marginal averages. These are the averages for the sleep groups collapsed across or ignoring stimulant. We can do the same thing with the reverse variable, because remember we have 2 variables going on here. Sleep, and we also have stimulant. So I can ask for the marginal means or the summary statistics for each of the 3 stimulant groups. Here the sugar pill average was 19, caffeine pill average was almost 23.5, 24, and the electric shock average was 21. Electric shock / money payment. So those tell part of the story. Your marginal or averages for rows or columns tell you some of the story. But the averages within the cells can sometimes show a different story. And this is the idea of an interaction. So here I've taken my table and I've put those numbers onto the edges of my table. Margins can be thought of as that's why they're called marginal totals. So for the control group, its average is 25, and I put the sample sizes. I've left off the standard deviations because I didn't want to clutter it so much. So the blue numbers are going across for the rows. The pink numbers are going down in the columns. This gray corner, I have the grand mean, and what's our total sample size? 60. Since there's only 3 stimulants, each stimulant has 20 in it. Since there's 4 sleep conditions, each one gets 15 because the 60 people have to be split up evenly. Now, I'm going to take each of these cells and I'm going to take the 5 white numbers, the actual scores, and I'm going to put the cell averages in there. Cell averages. Now, having all of the numbers there is great. That shows all of our data, but it's hard to kind of get an idea of the trends or the overall effects. Averaging is a way to simplify things so you can try to pick up on trends or relationships. So here I've put just the averages for the 12 cells and for the 4 row margins, the 3 column margins, as well as the grand average overall. And looking at this many numbers, frankly, my brain's like crashes and burns. What's a better way to look at a lot of numbers?
Plot.
A picture, a plot. So we're going to go ahead and plot this. So here I've kept my numbers over here. These are all the averages. I'm going to do plots of the average. So I can look at the main effect of sleep is looking at the averages of the sleep groups ignoring stimulant. And so the way I would plot it, I would put on the x-axis the sleep variable and the y-axis the score, and I can do stat summary, and it will put those points. We call this a means plot. It has the little arrows or the lines. Do you remember how far they go out? By default, they go out 1 standard error. So if we look at our averages, what's the trend with the averages? As we move to each more restricted sleep condition, the average goes down. This is the main effect of sleep. Notice when we say main effect of sleep, where's stimulant? Stimulant's ignored when we're talking about the main effect of sleep. We can do the other way around. I can look at the 3 stimulant averages ignoring sleep. Now we saw these in the blue and the pink numbers, but putting them on a plot can help us digest it a little more easily. So these are main effects means plots. Now, what each of these margins only have 3 or 4 numbers. My brain can do pretty good with 3 or 4 numbers, but 12 numbers, that's where my brain has a croaks. So these 4 numbers I will plot all together. And this is called an interaction means plot, when you have 2 different things going on here. So the way I did it is I have one of my variables on the x-axis, and the other variable is I chose to do different colors and shapes. Now, if we look at this above this first x-axis point, this is own schedule sleep. All 3 of those points are high, right? Whether they're on, who does the best when they're on this, which stimulant group does the best when they're on their own schedule of sleep? Who does?
The shock group?
The shock group. They do the best when they're on their own sleep. But is it that much better than the other 2 groups? There's this overlap with the standard error. So I'd say it's not a significant difference. At least my eyeball test would say. My eyeball test said, when I look at this, says in my own sleep, when everyone's allowed to get their own amount of sleep, there's not any real significant difference, although the electric shock payment group tends to be slightly higher, but it's not probably statistically significant. I don't have a p-value yet, but that's what I think. What about the jet lag group? Looking at just the jet lag group. Who's doing worse?
Placebo.
The placebo, the sugar pill, but it looks like offering a reward or having caffeine or this electric shock reward thing, they both are doing a little bit better than the sugar pill. Now, what happens when we go to interrupted sleep? Do we see the same pattern? Who's doing the best now?
Now the caffeine's significantly higher.
Yeah, in both of these last 2 sleep groups, the caffeine group's doing best, and the other 2 are about the same. So what's the ordering of the groups? Which stimulant is best?
It depends.
Hallelujah. That is an interaction. What did you say, Melissa? I thought it was you.
It depends.
It depends. The ordering of the stimulant groups depends on which sleep condition you're in. Which group is doing best or worst depends on which combination you're in. It's a combined effect. We cannot say across the board, sugar pill's always worse or caffeine's always best. Is caffeine always best? No. Sometimes caffeine is doing significantly better. Sometimes it's not. Sometimes electric shock is on the high end. Sometimes it's not. So that ordering depends on not just one variable, but 2 variables. The 2 variables interact or moderate the effect of each other. The key word here is moderate. The effect of the stimulant is moderated by sleep, or we could say the effect of sleep is moderated by stimulant. It's a 2-way relationship. Usually we use the phrase is moderated by, and it makes you think one is acting on the other, but mathematically we just say that they are interacting with each other. It's like a 2-way relationship. The choice of saying which one moderates the other one, that is a contextual choice you make, but it's a 2-way interaction. So we're gonna see.
Hey Sarah, how do you do this plot, the interaction plot in R?
I'm gonna show you on the next slideshow.
Oh, okay.
I should have put it on here, but I didn't. So we're gonna do degrees of freedom tree. I think I'm gonna wait and show this on the next slide, our next slideshow. But I want to show you the code in R so that you don't have to worry about this as we go forward. So we're going to do almost exactly what we've done before. If you look at this code, I'm saving it as a name. So I have that assignment arrow. I'm starting with the name of my data set. I'm still going to use the affix AOV4 command, just like a one-way ANOVA. Just like a one-way ANOVA, we start with our continuous interval ratio dependent outcome variable name, tilde wave, but look what comes after the tilde wave. Not one variable name, but two variable names, both of the factors, both of the grouping variables, and what's in between both of the variables' names. It's an asterisk. An asterisk stands for what math?
Multiplication.
Multiplication. An interaction is a multiplicative or a multiplying effect. So we use the asterisk between the two variable names for a two-way ANOVA. And we still have to tack on that one observation per ID, per person. That's the part we're going to tinker with next week when we do repeated measures. But today it's still one observation per person and data equals dot to pipe it from above. Syntax almost exactly the same as last chapter. That's good news, right? The last two chapters. Okay. So here I'm asking for the output. And I've done that by putting the name and doing that $capital A ANOVA to give me the fuller ANOVA. And we always ignore that intercept line. That just tests if the grand average is bigger than 0. Of course, this grand average is more than 0 on this because everybody had a score of at least, what, 11? So that's not important. So we look at the rest of it. Notice on our Anova table, we have a line for sleep, a line for stimulant, and then sleep with a single colon stimulant, and then residuals at the bottom. We still have sum of squareds, degrees of freedom, F value, P value. How many P values do we have? Not 1, and actually not 2, but 3. We have one for the main effect of sleep, main effect of stimulant, and the interaction between sleep and stimulant is how you read that. So if you look at the main effect of sleep, is it significant? Check its p-value in the little stars. Yes. Main effect of stimulant. Yes. The interaction between sleep and stimulant. Not really, because it's not less than 0.05. 0.08 is really fuzzy land. And then the residuals at the bottom. Okay. This is how the traditional ANOVA table would be set up. I'm not going to focus too much on this, but this table from R, it shows you the sum of squared, the degrees of freedom. It does not show you the mean squared. But how could we get the mean squared? Always mean squared is sum of squared divided by its degrees of freedom. So you could fill this out if you needed to, but nobody publishes this, so I'm not going to worry too much about that full table.
Sarah?
Yeah.
So what is it where it says like the sleep colon stimulant and that p-value not being significant? What does that mean exactly?
That means the effect of sleep is
it's not significantly greater than
not significantly different among stimulants, and the effect of stimulant is not significantly different among different sleeps.
Okay.
Sleeps, that's funny. My kids,
okay.
3 more sleeps till Christmas. Remember the sample size in this. We have 12 groups, and 60 might seem like a big sample size, but remember, how many do we have for each combination? Only 5, and that's why even the picture might look like there's an interaction, and then you're surprised this p-value is not significant. And it's probably because this toy data set only has 5 people per combination, and that's kind of small.
Okay.
But here in the green lettering, I said, if we had the interaction was significant, if. It's not, but let's pretend like it was, then you should not generally interpret the main effects in isolation. If you have an interaction, that means the effect of one of the variables depends on the other variable. And so you shouldn't look at one variable alone. That's the rule with interactions. You have an interaction, they're a partner. You can't look at one without considering the other.
Right. Okay.
So,
this right now, it is saying that there's a we can interpret the sleep main effect and the stimulant main effect because they were both significant and the interaction was not.
Yes. So yes, so strictly, if we're going to say this interaction is not significant because the p-value is bigger than 0.05, which we usually would, then we could say there is no evidence of a significant interaction, and then you can go on to interpret the two main effects on their own. And you would say there is an effect of sleep and stimulant, but there's no interaction. And then you can probe each of the main effects by doing post hoc tests, either pairwise or contrast statements, looking at the plots. We already looked at some plots that would help us. We could do all pairwise for those. We didn't have an a priori before we gathered the data contrast setup. Now let's play the what if game. What if we're going to pretend like that interaction was significant? We know how to do post hoc test or follow-up test with one-way Anova. We can do pairwise and contrast statements. If you have an interaction that's significant, you probe the interaction mostly by making a plot. I mean, really, you have to make a plot, really. But we get a p-value by doing what's called an interaction contrast. And these are slightly more complicated than the ones we've done before. And what you have to do is you have to, how many combinations did we have? 4 by 3, we had 12 combinations. You have to pick out the most extreme set, in that we're going to choose 2 levels from each factor that are the most extreme. So here I brought back our little table, our green 12 cells with the 4 blue and the 3 green marginal averages. So I'm going to go and I'm going to reduce down to the most extreme. So I'm going to look at, here's a research question. Does caffeine have the same effect in the no sleep whatsoever and the normal sleep? So I think we'll all agree that the most extreme sleep situations are none and normal. So we're going to choose those. And I really want to zero on caffeine's effect because, yeah. So I'm going to look at caffeine. So I'm going to compare caffeine to the placebo. For right now, I'm going to hold off on that electric shock because I just don't want to go there. So I'm going to zero in on that part of my table. Notice how I grayed out the rest. So I'm going to look at the 2 columns for placebo and caffeine and the 2 rows for normal and sleep. You've got to go down to 2 of each factor, 2 levels of each factor. Now, if I take those 4 numbers out, I can make a smaller 2 by 2 table. And this is what we're going to focus on for the interaction contrast. Again, we're going to choose a pair of stimulants and a pair of sleeps to come up with this little 2 by 2 smaller subtable. And we're going to say, is there an interaction in this 2 by 2 table? So if caffeine has an effect, then the difference between caffeine and placebo, we want to know, is that difference the same? When you have, so when I have normal sleep, look at the top part of that table. When I have normal sleep, how much higher is the caffeine average? Kelly, I see your mouth, but I don't hear because you're muted.
I just said it's not much.
It's not much. It's like 0.8 higher. But in the no sleep, what difference does caffeine make?
7.2.
7-point difference. Now we want to get a p-value to say, is there a difference in the differences? Is there a difference in the differences? Does caffeine's different? Is it a consistent difference or is it an inconsistent difference? Is there a difference in the differences? It's like a double negative. What do we get with a double negative? Positive, right? Okay, so this is my linear contrast. In the purple bubble, I have caffeine's effect in the normal sleep, and I subtract those. Now, the little 1s and 2s have to do with the first or the second, and first it's row, and then column, they're the indices. So what happens when we have subtraction, and we're subtracting both subtractions? This goes back to algebra class, right? When you distribute the negative, a double negative makes a positive here. So we have a minus, minus, plus, because we're doing the difference, that's the center difference, in the differences. Each parentheses has a subtract. Now, I don't like negatives any more than you do, but let's pretend like those are contrast weights. So I'm going to, instead of having a subtract, I'm going to have add a -1, because that's doing the same thing. So now in red, I put the invisible coefficients, the numbers. So this x bar 1, 1, there's nothing in front of it. So that's an invisible coefficient of 1. So 1, this said subtract, so that's like plus a -1. Here's another subtract, so that's plus a -1. And then this is a plus, so it'd be just a 1. What are the 4 weights we have now? 1, -1, -1, 1. Those are the weights for an interaction contrast always. 1, -1, -1, 1. I have them up here in this teal box. They're always going to be that way for an interaction contrast, because we're always seeing the difference of a difference. And that makes the last one a +1. What happens when you square those and add them up, those weights? 1s and -1s, they all square up to be 1s, so we add them together, we get 4. So if we do I'm only doing the longhand math to show you, and then we're going to use R to do it for us, because, you know, lazy. No, accurate. We're going to do it for accuracy, not laziness, right? Okay, so I'm going to take my averages out of my little 2 by 2 table, and I'm going to times them by their contrasts and add that up, and that's what I get for my L, my linear contrast weight. To get my sum squared, I do my number per group times L squared divided by the sum of my C squareds. The only complication here is what's N. N is the number for each cell. So the cells each had 5 people. So we do 5 times my linear contrast number squared over my sum of my C squared. So that's 51.2. That's the sum squared for the contrast. The degrees of freedom for the contrast are always 1. And we make our F by taking this sum squared and dividing it by the mean squared within. The mean squared error is just like before. And we get an F value for our contrast statement. Now, for interaction contrast statements, if they're not defined a priori, we have to do a correction, and we're going to do Chaffee's correction. And this is one that's on your formula sheet. We did one-way Chaffee's before. Now we're doing two-way Chaffee's. And basically, you take the interaction degrees of freedom and you times it by the F value, critical value you would look up in the table. The degrees of freedom for the interaction here is for the two-way Anova, not just the 2 by 2 table. And we'll see how to find that when we go back to the other slideshow. But looking at this, my F for my interaction contrast is a little more than 3.12. My Chaffee's critical value is 14.4. Is the interaction significant? Did my F value make it past my Chaffee's critical value? No. So this is saying, even though when we subtract those, we say placebo made a little effect, tiny effect in the normal sleep and a substantial effect in the no sleep. It seems like that, but that's ignoring the sample size and the standard deviation. And when we put all the information together, we have no evidence of an interaction.
I got a little bit lost.
Yeah.
When I don't know, somewhere between making the SS contrast to figuring out the F, I thought it was the opposite. I don't know, I got lost.
Okay, good news is, Michelle, we're not going to do this by hand, okay? So we'll learn how to put it into R. This is what it looks like on the plot. Here is the normal sleep. How much different are the dots for sugar pill and caffeine? They're only 0.8. How much different are the points when we look over here for total lack of sleep? They're different by over 7. But when we did a p-value, it says that those differences are not different. There's no evidence that the differences are different. So it's more like those lines are essentially parallel based on the data we have. Now, it's not saying that that's impossible. We just have no proof that those lines are not parallel. They're not different enough. Okay. Are you ready to see more of the in-depth? Does this help make sense? Now, this example was in the book. Does this make a little more sense than when you read it? Or you still have questions on this example? Because this is a really great example. See some thumbs up. Yeah. Brian, we're good? Okay. I can't see you all at once, so I have to keep scrolling down your pictures. I can't see everyone at once. Okay. All right. So let's go on to the actual chapter 14 slideshow that is here in the Two Way Anova PowerPoint. Now, this is a very long slideshow, and I don't anticipate we will have enough time to do all of it, nor would I want to bore everyone going through it. I would really love to have some time at the, today to start on some of the homework questions and allow you to have some question and answer time for that. So we're going to just hit some high points. So that means that you guys, if there's, when we get to something that you were like, wait a second, I wanted to ask about that, or that was really confusing in the book, please stop me, okay? So this is, I don't want to just rush through it all for the sake of rushing through it all. Okay? And put you guys right there so I can see you. Okay. So again, going back to square run, the idea with the two-way ANOVAs is we might want to do, like this Dr. Petrov is interested in looking at 30 high school students randomly doing a computer simulation tool versus 30 students doing the lecture pencil paper problems. So we got two kinds of learning strategies going on here. Usually, up till now, we would have done a one-way ANOVA with K equals to 2 groups, the computer simulation group and the standard lecture with paper pencil problem solving format, K equals 2. But what if in additional to wanting to see how the curriculum teaching strategy has an effect, he also wanted to look at the effect of sex. Here, this is where we have not one, but 2 factors we want to investigate. The first factor would be the teaching method. And so if we're going to make columns in our table, again, it doesn't matter which one's columns, which one's rows, but I'm going to choose to make column based on teaching strategy. We would have 2 columns. So we use, instead of K equals 2, we call it C equals 2 because we would have 2 columns. And then sex, we would make as our row variable. And say we were going to do male, female, and other. So that would be 3 rows in our table. So R, this is not correlation R, this is just R for row, we'd have 3 rows. This becomes a R by C. We always do R by C because it's rows by columns is matrix math. So this would be a 3 by 2 ANOVA. 3 by 2 factorial ANOVA because we'd have 3 rows and 2 columns. Now you could have done it the other way around. So a 2 by 3 is the same thing as a 3 by 2. It doesn't matter which one's first and which one's second, which one's rows, which one's columns, as long as you're consistent within a problem. So previously we did one-way ANOVA. Today we're doing two-way. But you can do 3-way and even 4-way. It gets a little complex and you've got to have a good sample size for every combination. And that's what usually limits us from doing a lot of 3 and 4-way. Because if you have, in a 2-way we saw, you have 3 levels and 4 levels, that makes how many combinations? 12, and you probably need a good sample size for each of the 12 combinations. So your what if we had a 3 by 3 by 3? 3 times 3 is 9 times 3 is 27. Now you need a good number of people for each of 27 combinations. Then, you know, that's why we usually don't do 3 and 4 ways, but you could. Math works. So if I had a 2-level variable and a 3-level variable, we would call that a 2 by 3 factorial design. Factorial means all combinations. And that's what these 2-way ANOVAs require. They require all combinations. So if I had another one where I had 4 levels for my first factor and 2 levels for my second factor, that would be a 4 by 2 factorial ANOVA. And how many combinations would we have? 8 cells. Okay. So the place where we always start is a means table. So here I've set it up with the 2 different learning strategies, the computer simulation tool and the lecture paper pencil problem. And then the 3 rows are for male, female, and other gender. So I've got margins for the rows, margins for the column, and then in gray, I've titled it the grand mean. The grand mean is the average of all of the entire data, all of our entire sample. So if we average each row, that gives us our row margins. If we average each column, we get the column averages, and each of the combination cells, those are called cell means. Now I've used orange and green in this scenario. Orange for the rows and green for the columns. And when we're looking at the mathematical formulas, a lot of the formulas use double subscripts on the means and sometimes the standard deviations. When there's 2 number subscripts, the first number is always for the rows, the second number is always for the column. So this first M on the upper left-hand corner says M11, so that's the first row, the first column. This last lower right-hand corner M, it says 32, so it's the third row, the second column over. Now notice on the margins, how many numbers are subscript on the margin needs? There's only 1 number, and then there's a dot. The dot either comes before or after the number, and the dot is for what it's averaged over. So this is M1 dot, so it's first row averaged over both of the columns because the dot is the second number. Down here, this is M dot 1, so the dot is first, so that means averaged over all the rows, the first column. So you could call the grand mean M dot dot, and some people use that abbreviation for it. Okay. You'll see the dot dots in some of the formulas. So the idea with the factorial ANOVA is we want to look at simultaneously at the same time 2 or more factors. So we want to know, does way I teach make a difference, and does sex make a difference? We want to investigate 2 things at once, but it's more than that. Not only do we want to know, do these 2 things have an effect, but we also want to investigate the interaction between the 2 factors, and that's the strength of a two-way ANOVA. So when we cross-classify, that means each person in our study belongs to one and only one, mutually exclusive, one row factor, one level of the row factor, and one level of the column factor. So when we did the first example slideshow, everyone had to be in 1 sleep condition. They couldn't be in 2 sleep conditions. They had to be in 1, in exactly 1. And everyone had to be in 1 stimulant condition. They couldn't be in 2, they couldn't be in 0. They had to have 1 of each. So they were in a unique combination. Now, who started the homework? You guys start the homework? No? The first few on the homework are some really, really toy data sets. And they ask you to look at this little table. It's a little teeny tiny 2 by 2 table, little tiny. And they ask you to decide, is there a row effect? Is there a column effect? Could there be an interaction? The way you tell if there's a row effect, you look at the row margins. So you look across the rows and you say, do the rows have the same average? So the first item on the homework, you're just going to say, are the rows have exactly the same average or not? And that will tell you if the row variable has an effect, a possible effect. We don't know its p-value yet, but that's testing if the averages in the population for the row variable are significant. You look at the row margins. So if I wanted to know, is there a main effect of the column variable, what would I compare? To know if the column variable has an effect, I would look at the columns averages to see if they're the same or different. The tricky one is looking for an interaction. When we look for an interaction, we want to know, does the pattern in the cells, is it the same on every row? Is it the same in every column?
For the interaction for the row and the column, if they're different at all, there's an effect.
You can have an effect, main effect of the first variable, a main effect of the second variable, or an interaction, or any combination of those.
Yeah, but what I'm saying, so if I was looking for a row effect for that main effect, if they're not the same, there's an effect.
Possible. It depends. So it's like when we did a t-test. We wanted to know, are the averages different? The averages are always different in the real world. We want to know, are they different enough? So when we're looking at those row averages and the column averages, we want to know, are they about the same or are they substantially different? And the first item on the homework just has you eyeball it to see if there's a possible effect. The way we know if there's effect is we actually do the Anova analysis and get a p-value.
Okay.
Yeah. So with the interaction, we want to know, does it depend? Do the averages in a row, are they different on each row or are they same on all rows? Are the averages in the column the same in all columns, or do the averages depend on which column you're in? So we're, again, in a table, average table, we're going to look on each row and say, are these averages the same? Is this pattern the same on every row? Is the pattern the same in every column? We want to know, is the pattern the same? Now, like we just said, Melissa, you can have main effects for each variable and the interaction between the variables. So there's 3 things that can possibly be significant or non-significant. And you can have any combination. Just because you have an interaction doesn't mean that the main effects are still significant. When you're going to say what the results mean, whether this is just for yourself or whether it's for writing up the results, you always want to look in this order. Number 1, you always want to look at the interaction first. I can't say that enough. Always look at the interaction first. If it's significant, you have to interpret it first and use extreme caution if you even look at the main effects. An interaction in importance trumps main effects, always. And I think that's something in social science that is sometimes overlooked. Because remember, what does an interaction mean? The effect of one variable depends on the other variable, so you can't look at them in isolation. So after you look at the interaction, if the interaction is not significant, then you go on and you look at the main effects. And you could have both main effects, rows and columns, they could both be significant, or only one could be significant. Or you could reach the third thing where nothing's significant. But always, what do you look at first? I'm gonna drill this. First, you look at the interaction. I saw some lips moving, thank you. Okay. I'm gonna skip that, okay. So when we do an ANOVA, what is the bottom of our F statistic? What goes on the bottom of our F statistic? What number was that? The mean squared within. That's the mean squared error. That's the like noise variance. The bigger that number is, the less powerful our study is. And subject to subject variability makes that mean squared error big. So if there's is a factor that explains some subject to subject variability, including that into the model, increases our power by decreasing our mean squared error. So we want to include in our models things that explain variance. So this teacher could have done a one-way ANOVA, or even a, oh, thank you, even a t-test looking at the two teaching methods, right? But being a geometry teacher, because I was once upon a time in high school, I know that it's not just about how you teach, how kids do. There's a lot of other factors. And one of the factors is gender. Is it the biggest factor? No, but we'll use it for today. Gender has an effect on how well kids do in geometry, because especially at that age that you're usually teaching geometry, the boys, don't want to be like cool math nerds. That's not a thing. Anyway, gender can have an effect. So gender can account for some of the person-to-person variability. So if I include gender in my model, then that person-to-person variability that's attributable to gender can be pulled out of the mean squared error. The mean squared error shrinks and our power goes up. Now, what if I included a variable called eye color in the model? Does eye color have anything to do with teaching method and geometry score? Probably not. I'm pretty sure it wouldn't. And if you add a variable into a model that has nothing to do with it, you cost degrees of freedom and you don't gain anything by reducing the mean squared error. So you don't want to use variables that are not predictive or that don't account for variability, because they'll hurt your power by sucking up degrees of freedom. So sometimes we know variables that can have effects, sometimes we don't. If you don't know what variables have can account for variability, one thing you can do to strengthen your research is to do a repeated measures design. That's not always possible, but that's one way in which each subject becomes their own control. Now, can you teach geometry to the same subject with two different methods? Probably not, because the first time you teach it, they're going to retain something, and it's not like starting from scratch the second time. And you'd have to do a different chapter. So might not even be possible there. But that repeated measures design is one way to try to control or to reduce your mean squared error. And we'll talk about that next week. So assumptions. We're speedy, right? We're almost ready to take a break. Am I right? Right, Lara? So assumptions. These look really, really familiar. Assumption number 1, independent observations. Number 2, normally distributed outcome in each population. But now it means each cell. And homogeny of variance. But we don't just have K groups, we have R times C groups. So independence, how can we test that? Can't test it. We can just plan to sample the best that we can under the conditions that we have. How do we check for normality? Histogram, QQ plots. We could do side-by-side box plots. If we really want to get technical, we could use what test? Shapiro-Wilks. And the last one, homogeny of variance. How do we check homogeny of variance?
Levine.
Levine's test. How much new stuff here? What's the new idea today? Interactions. Mostly everything else is the same. Okay. So let's look at the F-test, because now not only do we have one F-test, we now have 3. The interactions and both of the 2 main effects. Okay, so here's our old Anova table. Remember seeing our old Anova table? We had between groups, within groups, and the total. Now we're going to have a little more complicated Anova table. What's happened? Is it the same? It's got the same columns, but it's got a few more rows in it. Instead of having just K groups, we have R rows, C columns, and all the combinations for the interactions. So we have, instead of the 1 F-test, we now have the 3 F-tests. But the mean squared within, the within column is still going to be our denominator for our F-test, still the same. So I've highlighted first the sum of squared columns. Now, let me see, how mean was I on the homework? No, not mean. You have to do one of these by hand. And hopefully we can get to it together so it's not too painful, okay? So the sum of squared, there's two versions to these formulas. There's the version that we use with summary statistics by hand, and there's the version that does the raw data computations that the computer uses. But in general, when we had the one-way ANOVA, we took the total variance and we partitioned or divided it up into that which was variance between groups and the variance within groups. We made those two, that separation. So we have sum of squared between groups and sum of squared within groups added up to the sum of squared total. That was with one-way ANOVA. With two-way ANOVA, we're still going to do that, but instead of having K groups, we have R rows, C columns, and the combination for cells. So we still have the sum of squared is the total variance, and we have sum of squared within, but now it's within cells instead of within groups, because these are the combination groups are the cells. And instead of between groups, our 1F statistic and one sum of squared, we're going to break it down further into first variable, second variable, and their interaction. I don't know how someone came up with this, but it's beautiful math. Makes me, oh, I math fangirl over this kind of math. Okay, so here's the row variable. The sum of squared for whatever our row variable is. So if our row variable has two groups, how many means are there? Two means. If our row variable has three levels, male, female, other, how many means are there? Three. If my row variable is sleep, regular sleep, jet lagged, what was it, disrupted, and total lack, how many averages do I have? 4. So this is what you do. You take your, however many rows you have, you take your rows averages, you take each row's average and subtract the grand average. Is something feeling familiar? And square those. When you subtract them, why do we square? So they don't add up to 0. That's why it's sum of squared, because if we just summed, it would always be 0. So we have to square it to make it so they're all positives. And then we're timesing it by the number in the row. That's how we get the sum of squared for the row. We did this before for groups. We took the group three group averages minus the grand average, squared them, added them up, and times by the number in each group. It's the same formula, but here we're doing it on the row totals, the row averages. Now this top one is the one that you would do if you knew the averages. This bottom one is how the computer does it. Same math, glorious math. Okay. So that's how you do the row variable. Guess how you do the column variable?
Same way, but with columns.
Yeah, look, it changes color. Orange for the rows, green for the columns. Yeah, the same way you take the column averages, however many there are, subtract the grand average, square them so they're positive, add them up, and now you times by the number that are in each column. Now notice I'm saying each column as if each column had the same number. That's because ANOVA is based on the idea you have balanced data where all the cells have the exact same number. Each combination gets the same number. Now, in human subjects design, what happens? People drop out, they decide not to participate, even if you plan to have equal number groups, that goes out the window. We'll talk about that at the end. But we're gonna plan on having the same number in every combination. Okay, so row and column variables. To do the main effects, it's just like we did with the grouping variables before, as far as math goes. The interaction is a little bit more complicated. So here I got orange for rows, green for columns. Now I got purple for those cells. I'm using the same colors in both slideshows because I'm OCD like that. So the way you do that is now you have to look at the cells. For the interaction, you look at the cells. So say you had 5 by 2. How many cells would you have there? 10. So you take all 10 cell averages, subtract the grand average, square it, and times by the number in each cell. We've done that before, but then you have to subtract off the SSR and the SSC, because if you don't, it gets double counted. So this formula is a little different. You do it based on the R times C, whatever number cells, but you have to subtract off the sum of squared rows and the sum of squared columns. So you calculate those first. Does it seem like a lot of math?
Yes.
Yeah, who wants to do this by hand for the rest of your life?
Well, are we doing this by hand for the test?
No.
Okay.
You're doing it on the homework, and here's the thing, it even tells you the interaction is 0. So you know that this sum of squared RC is 0 for the one that you have to do by hand. After that, it's always done with R, because gag me. I mean, what's the likelihood you would do all that math perfectly every time? With me, like it's
Pretty
0.
slim.
In fact, I would bet I would make a mistake in like the first.
I did like Cohen's shortcut on the calculator. It made it much easier.
Yeah, but still, this kind of stuff is like, gag me. I don't want to do this by hand. I'm not an arithmetician. I'm not one of those like calculators. I want to know, is there something going on? I don't want to spend my life adding and subtracting. I'd be an elementary school teacher if I wanted to do that. Ugh. Okay, so yeah, so there's some shortcuts for doing the mean squared within. And basically, mean squared within is a pooled variance number after accounting for the other numbers. So my favorite is this last formula. You take the total variance, the total sum of squared, and subtract those 3 pieces, and then you end up with the sum of squared within, which is what I would do by hand. I think the one on the homework is it has you do, it's only a 2 by 2, so this is small, so we can do it by hand. Okay. So let's go to degrees of freedom. So we talked about the sum of squared. There are great, beautiful mathematical formulas that we don't really want to do by hand much, but they exist. The degrees of freedom, their by hand formulas are not so bad. So on the formula sheet that I put together for you guys, there are these degrees of freedom trees. So I have the one that's uncovered here is the one-way Anova. So we took total and divided it into between groups and within groups. So the total degrees of freedom is total sample size minus 1. How many groups do we have? K. How many degrees of freedom for the grouping variable? K minus 1. And then the within groups degrees of freedom is NT minus K. All right. So let's see if we can figure it out when we have some more complication going on. So we've got over here I've got it hidden. We're going to reveal the degree of freedom tree for a two-way Anova. So the first thing we're going to start with total degrees of freedom is still total sample size minus 1. Remember, when we do a split, the 2 halves have to add up to the whole above it. So that can help us. So first we're going to split within cells and between cells. Now, what's K basically? K is the number of groups or combination groups. If we have R rows and C columns, how many groups do we have?
R times C. So RC. RC together means R times C. So between groups, we have R times C minus 1. And within groups, we have total sample size minus RC combination groups. Okay? We good there, Kelly? Did you want to say something?
No, I was just seeing how my spacebar unmuted it because everybody unmutes so fast, and so I just figured that out.
The spacebar? My spacebar does my PowerPoint. It's overriding that. Oh well. Okay, so that part is the same as the one way, except for instead of having K, we have R times C. Now we're going to split our groups into row factor, column factor, and interaction. How many rows do we have? Well, we use R, so how many degrees of freedom for the row variable? R minus 1. How many column groups do we have? C, so the degrees of freedom is C minus 1. And for the interaction, now this is the one that people tend to make a mistake on. It's not RC minus 1. It's R minus 1 and C minus 1 multiplied together. So if I have a 5 by 2 ANOVA, what are my interaction degrees of freedom? It's not 9. You have to do 5 take away 1, 2 take away 1, and then multiply it, and you get 4. Okay. What if I had a 3 by 4? This variable has how many degrees of freedom? 2. This variable has how many degrees of freedom? 3. The interaction would then have 6 degrees of freedom. Okay. All right, so if we know how to find the summa squared and we know how to find the degrees of freedom, how can we get mean squared? Mean squared is summa squared divided by its degrees of freedom. That is like an internal truth for ANOVAs. You can get a mean squared for anything by taking its summa squared dividing by its own degrees of freedom. Now this mean squared W, MSW, is also called MS within, MS error, MS residual, MSE. That's all the same thing to make you confused. No, it's just, people call it different stuff. So you know, if someone says the mean squared residual or the MS residual, that's the same thing as MSE. That's the same thing as MSW, same thing as MS within, same. We're almost ready for a little breaky break, aren't we? We're almost done. We're so close. Well, to break. Last thing before, let's do this last thing before we go to a break. How do you make an F statistic? It's a fraction. What goes on the bottom of every F statistic?
The mean squared error or mean squared
Mean squared error, mean squared within, that thing we just named 12 different things. And what goes on top?
The between.
The mean squared. Before we just had between groups. Now we have 3 different kind of mean squares we can put on the top. The mean squared for the row variable, the mean squared for the column variable, or the mean squared for the interaction.
Mm-hmm.
If we want to do the row variable, we would do the mean squared for that row variable divided by the mean squared within. So we're going to have those 3 different F statistics. Now, for those 3 different F statistics, all of them have the same bottom of the fraction, so all of them have the same denominator degrees of freedom. But all of them have a different numerator on top, so all of them have a different numerator degrees of freedom. So this is one place where you have to be careful when you're looking up your critical values. You might have to look up a critical value for your row variable and a different critical value for your column variable. But be careful with your degrees of freedom because it's not going to be necessarily the same. But the denominator is always the same, the bottom. Okay, so here's the formula sheet where I put all this stuff. Okay, no memorizing all these formulas, just know where to find them. Okay, we ready to take a break? We'll come back, we'll talk about effect sizes and writing up APA and get that homework started.
Sarah, can I ask a quick question about the due date for the test? Is
Yes.
that due tomorrow night?
We
We can talk about it when we come
come
back.
back, shall
Okay.
we? So
Okay.
let's go till 5 after,
Okay,
and then we'll
Sounds
talk dates.
thanks.
Okay. I'm reading the discussion, and I just read Kimberly saying that the last chapter in this one could probably be a semester-long class and just on their own. So true. Hillary, I love your comments. Awesome. Awesome, awesome. Okay, are we ready to come back? Ready or not, I guess I should say. It's time to come back. Okay. I have pulled up the Canvas syllabus due dates. So today was due the chapter 14 discussion board, and I just read through all of them. You guys had great comments. I love seeing how it's coming for you guys, and you guys are doing some great reading, and I totally know where you're coming from about this is getting hefty, especially section B of this chapter, really hefty. And that's why I want to get to where we're in the homework together so that I can help guide you along, because this is a little dense. It is, I mean, fact, but we're grad students, so we're going to plow ahead and get through it. So right now on the schedule, we have tomorrow are supposed to be due chapter 12, 13, and 14, and the 4th exam. So is that feasible? Melissa's shaking her head no. Kimberly's shaking yes. Brian, maybe.
Wait, can we have Wednesday for the exam too, though? I thought it was Tuesday and Wednesday.
Yeah, let's do it Tuesday and Wednesday for the exam, and then I'll make the homework due on Wednesday as well, because I don't want the homework due before the exam, because it does, yeah, we'll make it all the same. I can push it to Wednesday, and then I'll make Wednesday's discussion due on
Thursday? Friday? Okay.
Is that okay? I don't want to let it get too far away. I hate having the discussion due after the lecture, but there's only so much time in a day. What are we gonna do? You know.
So the homeworks and the tests, are they due Thursday night or Wednesday night?
Wednesday night.
Is Wednesday gonna be good enough?
Could we do Thursday? I mean, I'm hoping, but
Does not stop anyone from turning them in Wednesday. I will go Thursday. I can go Thursday.
thank you.
Is next week is our last week?
Last week. That's why I hesitate to push things too far. But if that was,
we have 3 tests. We have 3 tests left, right?
Yeah. Isn't that fun? This exam 4, I'll tell you straight up, is going to be probably shortest as far as number of questions.
Okay.
There will probably only be like 2 multiple choice and 1 interpretation situation where I give you output and you tell me what it means.
Okay.
Just because of your time, right? So I'm making this mark. So Thursday, you're going to have homework 12, 13, and 14 due, an exam 4. And then Friday, discussion on chapter 15, repeated measures. So that'll be Friday. And then Monday, have your discussion for mixed design. And then We can do Tuesday, we can change this to Wednesday, if that'll be helpful. Let's do that. Let's do Wednesday, the 17th, do homework 15, 16. I'll change these as soon as we're done with class if you don't want to write it down. Exam 5, and exam 5 will be like exam 4. A couple multiple choice, and then probably one situation where you have to interpret and write about it. And then the last day, so chapter 19 and 20, I'll just give you the heads up. 19, it's a whole lot of reading, and we're not going to cover a lot of it, just some basic ideas. So it would be probably advantageous. I'll push those discussion points off till Thursday. And I'm going to make that into one post, 19 and 20. And then we'll have already had class. Mostly we're going to the only thing in chapter 11 or 19 we're really going to hit is about the binomial is the sign test, because the sign test does get used. And then chapter 20 are all our chi-squared tests, our one-way and two-way chi-squared for independence and goodness of fit. So we've got, those are very important. We need to hit those. And then exam 6.
Is that possible to have over the weekend, or I don't know when you've got to get grades in?
See, I think I have till the next Wednesday to get grades in. So I could probably give you through Sunday to get that done. To do homework 19.
Thank you so much, Sarah.
And exam 6. You guys, there's so much more I want to do with you, and like I really wanted to have the exams like on the APA writing to have like I haven't given you any feedback on that because we've been running full speed ahead, and I wanted to have like a assignment where you could revamp your APA write-ups from the past exams, but I just don't think we have time for that. So what I will do instead is I will grade appropriately and I will give you one-on-one feedback on all of your exams, and I'll send that to you at the end of the class. Please ask questions and email things if you're not sure, because you're not going to get a lot of that one-on-one feedback until the end. I mean, I'll tell you, there's like, 90-some% chance you all are going to have A's in this class, provided you just kind of finish it up. I'm not worried about, are you an A- or an A+ or a B+. You guys are grad students. You guys are working really hard. This is an intense situation. I just want to get you the most benefit as you're moving forward in your program and into your own research. And in these 13 class days, we can get what we can get, and that's all we can get. So my door is always open to you guys in the future. I mean, I'm free resource for you as you're doing your research going forward. So please don't hesitate to contact me in the future, because that's my job. That's what I love. So you don't have to love it either, but that's okay. We can still be friends.
Sarah?
Yeah?
I'm just wondering, scheduling wise, would you be available for like an additional office hour tomorrow morning?
Tomorrow morning, let's see, let me pull up my calendar. I think I have something going on tomorrow morning. That doesn't mean all morning, but
Yeah.
like teasing me. Yes, I have an appointment tomorrow morning, 9:30 to 10:30.
Okay, and I have an appointment at 10 to 11, but
11:30.
I have another appointment at 11:30. Okay, so maybe tomorrow morning doesn't even work for me, but I'm just trying to think. I mean, because I'm planning on doing office hours tomorrow evening, but I'm just wondering if that'll be enough time for me to ask all my questions.
No, who was it? Somebody said on the discussion board that they watched my last year's office hours.
Yes, and that was super helpful.
So those are up from last semester as well. If you want the last semester's office hours on YouTube.
Yeah. Okay.
So if you want to go to YouTube,
I'll go look through those.
yeah, so go to.
They go through about half of the homework, not all of it, but about half of chapter 14.
Does it cover like the R stuff as well?
A lot of it, but I'm still going to go to the office hour tomorrow because there's still some of the R I'm not getting.
Okay.
Yeah.
But about half I got through.
Yeah.
So this playlist, the playlist is called Office Hours and Homework Q&As. So there's 2 of them for chapter 14. Oh, and there's chapter 14A number 6.
Oh, awesome.
Yeah.
Okay.
2 of those. And let's see, is this?
Yeah, I think I watched the lecture, but not the office
So there's
hours.
the lectures, and then there's these office hours and Q&A. So sometimes, you know, because this is when like everything went down last semester when we moved online.
Right.
So
Right.
we were like, what do we do? So yeah, so this A number 6, this is the one that I wanted to do together today because this is the one you have to do by hand. And
Okay.
the math isn't that hard, but there's a billion moving pieces. It's like a jigsaw puzzle.
Yeah.
And then there's these 2 for the other stuff. But yeah, but Leah, definitely come to office hours, and Laura, anyone else who can tomorrow night. And we can record that and post that for everyone else who can't make it.
Okay.
But if anyone else has a time tomorrow that is not when I have that meeting in the morning, I'd be happy to do an office hour. So as long as it's not 9:30 to 10:30. It's the only hour I have booked.
Yeah. Actually, I might be able to do 10:30.
You want to do 10:30?
Yeah, because I have a meeting at 10, but it's like just a check-in research meeting, so I can just.
Okay. Should we
Other
say
grads.
10:30 to 11:30?
Yeah,
Okay.
that's okay.
Okay, 10:30 to 11:30 tomorrow.
Okay.
Okay.
Perfect.
And can you record that and post it before your office hour in the evening?
I can. On Zoom, so when we Zoom record, it has to process it. Zoom has to process it to an MP4, and then I have to upload it to YouTube, and then YouTube has to process it. But so it takes a little while, but I will get that up as soon as I can.
Okay, awesome. Thanks.
Whatever. Sometimes it goes fast. Sometimes it takes an hour for each of the 3 steps.
Okay. Thanks, Sarah.
Yeah, and you can always email me with a separate question.
Okay.
Okay. Okay, should we talk effect sizes? So always, 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 as soon as you say there's an effect, you need to have an effect size to go with it. Again, I feel like usually you have to have an effect if you have a significant p-value. If your p-value is non-significant, we can debate whether or not you should have to report an effect size. It's always, you know, be on the safe side, just always report it whether or not your p-value is significant. So now that we've decided we need an effect size, which effect size do we need? Well, the one we used for one-way ANOVA was an eta squared, and it's called a generalized or an ordinary eta squared. And it's the summa squared for that effect divided by the summa squared total. So it's the proportion of variance accounted for by a particular factor or interaction. So we can have an eta squared for variable 1, an eta squared for variable 2, and an eta squared for the interaction. So those are the eta squared. So just like for one-way ANOVAs, we use the eta squared. And again, that's that Greek n that the bottom of the n kind of keeps going down. And when you type it in the test, you can just put a regular n. The ordinary n, eta squared. So again, we can have 3 eta squareds for a two-way ANOVA because of the 2 factor variables and their interaction. And these are the cutoffs that are generally used with an ordinary eta squared. About cutoff at like 0.6 and 0.14 for calling them small, medium, and large sized effects. So it's like about, if you have a eta squared of 0.03, that's saying like 3% of the variance in the outcome is explained by this variable. So Brian, you talked about how one of your factors could be branch of the military that your participants were in. So maybe the branch of the military that they're in accounts for a lot of variance, maybe a little variance. And so this eta squared would tell you what proportion or percentage of variance that grouping variable accounts for. Now, just like we said before, eta squareds are biased. We should be using omega squareds, and omega squareds are a slightly more complicated formula. And because of that, they are not used that often. They should be used, but people don't. The interpretation's the same. We use generally the same cutoffs. The good news is eta squareds and omega squareds usually come out to be close to the same number, maybe off by a decimal place or so. And because of that, people usually don't bother making an omega squared. But you could read about it. And maybe someday we'll get our act together and use omega squareds. But we're lazy right now because the software doesn't do it. We have a new thing going on here now that we're to two-way. The problem happens when you have all your eta squareds, they don't always add up sometimes. When all of your factors are experimental, meaning you've randomly assigned all your factors, sometimes our interaction is small too. So we usually, it's more appropriate to report what are called partial eta squareds. And they're the proportion of the variance accounted for by a particular variable or interaction, excluding all the other effects. And so if you look at these, that's still a fraction. And if we look at the ordinary eta squared, we have summa squared of our effect over summa squared total. These are summa squared of the effect, but the bottom is no longer the summa squared total. It's the summa squared for that effect and the summa squared within. That means that's error term. So it's excluding the other factors. And so this is usually what we use when we have a two-way ANOVA, is this partial eta squared. And just like that, you can have a partial omega squared, which gets to be a nastier formula than that. And if we look at the formula sheet, if you look at the lower right-hand corner, I've put both the ordinary eta squared, the partial eta squared, and then that estimated omega squared formula as well. R can give you both of these numbers. By default, it will give you GES, the generalized eta squared, which is the ordinary eta squared. But you can add a little bit of typing and it will give you both of them or just the partial eta squared. But again, in R, GES is the generalized or ordinary eta squared. PES is the partial eta squared. And you can report both of them or one of them. If you're going to report one, we usually go with the partial eta squared. Okay. We're going to look at some output in just a second so I can show you where you can find that on your outputs. So you don't have to do the formulas by hand because you. Okay. Interactions. So this was picked up on the discussion board, and I said it before. Interactions can be labeled with the word moderation. So a lot of times in social sciences, we talk about mediation and moderation. Mediation is something different. We're not going to go there. But moderation, it just means you have an interaction. When I started my job over here, I had people coming to see me all the time, and they're like, okay, I need to run a moderation analysis. I was like, a what? I mean, Kimberly, had you ever heard of moderation? In theoretical statistics and mathematical statistics, we don't use that word. But in social science, we use that word all the time, and I had to get like keyed into the lingo over here in this college that moderation just means an interaction. An interaction makes it clear that it's just mathematically the effect of one depends on the other, but moderation usually implies that there's A moderating B. But again, that's just a contextual idea. So we've seen two-way ANOVAs, and then you'd have a two-way interaction. You can, if you had three factors, you could have a three-way interaction. Those are very rare in ANOVA because you end up needing a giant sample size, because for all three-way combinations, you need a good number and your sample size needs to be bigger than you can get. So be skeptical of a three-way interaction in an ANOVA. In regression, it's easier because you don't have the balance requirement. So if you have significance of a variable, it means all the levels of the factor don't have the same average. If you have an interaction, it means the significant interaction, it means the effect of one factor is not the same at all levels of the other factor. So we just talked about that. So the best way to look at that is with a graph. And there's two very different looking kinds of graphs that are both interaction. So I'm going to throw these both up on the screen. Now, one of these, most people say, one of these is an interaction. The one that most people will point out as an interaction is the one where the lines are crossing. See the one where the lines are crossing? We've got a control group. In the control group, who has the highest test score? Average. In the control group, the highest average is for the high SES group. But in the treatment group, we have the reverse ordering. So this is the classical idea of an interaction, that the ordering completely reverses in one group versus the other group. And when you have that reversal of the ordering, you get crossing of the lines. This is called a disordinal. Dis means not an order. So the order is not the same order across the board. Now, an interesting thing, when you have a total crossing disordinal interaction, what happens if you ignore one of the factors? If you ignore a factor, that means you collapse across it. And if you collapse across it, you end up washing out the effect. So when you have a disordinal interaction, when you have crossings of the lines, this is a case where the main effects have no meaning. Because if you ignore one factor, like what would happen if we averaged the blue and the red dot on this side and averaged the blue and the red dot on this side? What would happen with those dots? It would be completely flat. And you would think that nothing was happening. So when you have a disordinal picture like this, and I so am a proponent of plotting your data, especially because R makes it easy. Plot your data. If it's crossing, that's a time when you totally want to interpret the interaction and ignore the main effects. Now on the other side, on the left side, we have an ordinal interaction, and we call it ordinal because the order remains the same. On the left hemisphere damage side, who makes more errors? Men or women? Who makes more errors on the left hemisphere damage?
Men.
Men. On right hemisphere damage, who makes more errors?
Men.
Still men. The order is the same. The order didn't flip, but what is different? The order is the same, but the gap is different. So you can have an interaction where there's no crossing in the picture, but the gap has different sizes. That's called an ordinal interaction. And that is just as much an interaction as a disordinal one is. Now, if you have an ordinal interaction, you might have main effects and they might be important to interpret. Here we could say that across the board, men have more errors, and across the board, left hemisphere make damage results in more errors than right. But it looks like left hemisphere damage is more detrimental for men than it is for women. Because see, what happens when you compare left and right for women? Left is a little bit more errors than right, but for men, left hemisphere is a lot worse than right. So the impact is enhanced in males. It's not the same. So ordinal interactions are still very important, even though they're not crossing and changing order. I think we could all agree in education, there are gaps based on socioeconomic status or ethnic group or other risk factors. There's a gap. Do we just want to reverse the order, or is closing the gap important? Changing the size in the gap is just as big a deal as perhaps switching the order. So closing a gap is just as important of an interaction. So we always, again, look at the interaction first, and then based on that, we shouldn't look at the main effects. If there's an interaction, okay, if it's an ordinal small interaction, then maybe we can look at the main effects, but that would be the only situation. Visualizing with the means plot is the best thing you can do. When we do the means plot though, before we put our predictor variable on the x-axis, our grouping variable, and our outcome, our dependent continuous interval ratio on the y-axis, But what happens when you have two factors, two independent variables that are grouping variables? One of them gets to go on the x-axis, but what do you do with the other one? That's what you base your shape, color, and line type by. And then you can show up different lines. The general rule of thumb, you've got to choose one variable, predictor, inner variable for the x-axis, and the other one to be the line type. You generally want to choose if the more ordinal factor to be on the x-axis, if it has more order to it. Like ethnic group doesn't really have order to it, so that would be a poor choice for the x-axis. And if you had dose, it was like low, medium, and high, that'd be a good choice for the x-axis. If something has ordinality to it, that's a good choice for the x-axis. If a factor has the more levels, it's a good choice for the x-axis. The one with, if one has 5 levels and one has 2 levels, choose the one with the most levels to be on the x-axis. That said, I usually will make it both ways. The first variable on the x-axis, the second variable for the line type, and then I'll reverse them. And sometimes one way will show a pattern more clearly than the other. And so there's not one right plot to make. So it's often helpful to do both. So the book had all these, and Brian, was it you that said you liked these? The visual representation. So this first plot was there's no effective A, no effective B, no interaction. They're basically the same line, flat line. And here, A1, A2, it's flat going across A, so there's no effective A, but B1 and B2 are different lines, so there's effective B, but the lines are perfectly parallel. Perfectly parallel lines means no interaction. So this first column are no interactions. The second column shows several different ways you can have an interaction. Notice, are all of those interactions showing crossing lines? No. And you can think about extending those lines further. Even the second one down with the interaction, those lines are not crossing, but what would happen if you continued to draw them out further? Eventually, they would cross. And sometimes that helps think about it, that eventually they would cross. Now, sometimes when we make a plot, it looks like the lines are not parallel. But how do we really know if there's an interaction? We need that p-value that goes with the interaction term in our ANOVA. Okay. So only look at the main effects. How many times have I talked about main effects not looking at them? It's like the third time. Do not look at the main effect unless there is no interaction, or if there's an interaction with extreme caution, only if the interaction has a small effect and it's an ordinal pattern. It's the only time you should look at the main effects. There's no interaction at all, or it's a very small effect size interaction that's ordinal. But you should still report everything. Even though we don't interpret the main effects, we would still report them. So what do we need to need? If an experiment on a drug had opposite effects in men and women, what would happen if we did the analysis ignoring sex? Men, it's like this. Women, it's like this. What happens if I ignore sex?
It would show no significant.
No effect. Yeah. So we always want to include anything we think might be a moderating effect. Even if the interaction term is non-significant, we can be more confident. So even if you had, like Brian, one of your variables was branch of the military, and you had some other variable, if there was no interaction, you might say, oh, well, it was kind of a waste to put an interaction in there. But it isn't, because now we can generalize. If there's no interaction, that means the effect is the same for all branches of the military. And that's good to know. So it's not good or bad to have an interaction significant or non-significant. And if you have a non-significant interaction, it doesn't mean that that was worthless to do, because it provides us information. So try not to think in terms of good and bad and exciting and wasteful. You still want to report the interaction because the fact that an interaction is not significant tells you information. Okay, so I told you when we did our first slideshow, we would look at probing interactions and those interaction contrast statements a little bit more. Right, Melissa? Because that's where you got lost, huh? Okay. Okay. So when we did the one-way ANOVA, we said our F statistic tells us overall if at least one group was different. When our interaction is non-significant, it tells us that the ordering or the difference between the means in one group is different than another group. And we need to probe it or do multiple comparisons to find out where the differences are. Because those F tests just say, hey, there's a difference somewhere over here. Look here, look here. It doesn't tell you the details. That's where we need the multiple comparisons. So we can look at where the differences are. So here's this slide. Okay, if, let's say you have no interaction, there is no interaction, and only one of your factors is significant, and it has two levels. Say it's left-handed, right-handed. Do you need a post hoc test to tell you which groups are different? If there's only two levels and it's a significant difference, there's only one pair, so you don't need to do a post hoc. What if it was three levels, left-handed, right-handed, ambidextrous? Now we need to do some post hocs to find out where. So one way to do the post hocs is to do what's called a modified one-way ANOVA test. And this is done by hand. I don't see this done very much. So I'm gonna kind of skip over it. What I see done more are interaction contrasts. And these are a little bit confusing the first couple times you do it. So I think that slideshow that we went over where you take, remember we had that grid that was 12 combinations and we chose 2 extreme rows and 2 extreme columns, and then we made a smaller 2x2. And what were our weights in that smaller 2x2? We did a difference of differences. It was 1, -1, -1, back to +1. So I'm going to show you how to do that in syntax. Okay, so if you have a significant interaction, we follow the interaction up with interaction contrast statements. If your interaction is not significant, you just look at the 2 main effects one at a time. So first we would look at one variable and we would do it, if it has 2 levels, we just say that their 2 levels are different. If it has more than 2 levels, we would do our either the one-way ANOVA, or we can do pairwise and linear contrast statements that we learned to do before in chapter 13. I think we need some examples. We'll do some examples. Okay, we'll do the section C. We'll do section C. Okay, let's talk APA. Good. We're good. We got like 40 minutes. Awesome. Okay, APA results. What needs to go in your APA results? Methods results. What do you think we need to put in there? What are some of the things?
The type of test.
Type of test. What?
Number of participants.
Number of participants.
Different variables.
What's our dependent variable? What are our 2 independent variables? What are the levels of each of the independent variables?
Homogeny of variance.
Assumptions like homogeny of variance.
Somebody else can take it from there.
Laura gets what, 5 gold stars there? Boom, lots of them. Okay, let's see. Generally, we want to include the means. Now, this does not mean you need to write all the means and standard deviations in sentences. Usually we make a table with the means. That furniture table 1 function, it makes a table with the means. Slick. Usually we'll say, see table 1, and you can describe the means instead of having to put all those numbers in parentheses and filling up your sentences on your page with all those numbers. Just make a little table. refer to figure 1 for the means of each group, right? You do not generally need to report the mean squared within, the mean squared error. I don't know if the book did. The book did for one ways. We usually almost never do for two ways. It's not going to hurt to throw it in, but it's just not generally needed. For each effect, for both of the factor variables and their interaction, you need to include the F value with the its degrees of freedom, which they're all 3 F statistics are going to have the same degrees of freedom within. They'll have maybe different degrees of freedom numerator, and they're all going to have their own F value and P value and at least an eta squared. And then we need to report any post hocs or planned comparisons. We follow it up. So just like a table is really helpful for the means, even better is a figure. Figures are really helpful because we get so many numbers going on. Okay. Now, some people brought this up on the discussion board. What about the, Cohen liked to talk about unbalanced sample size, right? He goes on and on about this, right? Here's the good news. The software handles the formulas for you. This is what you need to know. All the formulas are built on the idea that we have complete balance, that every combination has the same number of people in that combination. That makes the main effects and the interaction, makes those what are called orthogonal designs, which is a good thing. But if you have unbalanced, meaning you have a different number of people in some of the combinations, which happens with human subjects, then we lose that orthogonality. The more unequal the group sizes are, the worse this dependence or correlation of factors ends up being. And what it does, the imbalance makes that those sum of squareds don't add up to the sum of squared between. It makes it more difficult to do the work, but R handles it beautifully. So here's a picture. For balance, notice here's our dependent variable. Each of the factors, factor 1 and factor 2, and the interaction, they all account for some of the variance in the dependent variable. Notice how these circles are all not overlapping. They're all separate. This is if you have all of these add up, nice. But if you have unbalanced, different sample sizes, the bubbles, it's like they're overlapping and stuff gets counted multiple times. And so you have to change the formulas. And it's kind of messy math, but R will do it for you. If you just use the same Apex Anova, it will handle it for you. The adjustments that it does, it uses a harmonic mean, which I kind of briefly mentioned the other day for the group sample size. It does some weighting for the mean squared. You can do it. I find the bigger problem when you have human subject design is homogeny of variance is often violated. And homogeny of variance violation is more of a concern with an ANOVA. And so the best thing to do if you violate homogeny of variance is don't do an ANOVA, do regression. And that's the next class you're gonna take, right? We're all gonna take regression next, 7610. And even think about multi-level modeling, 7650 that I teach in the fall. It's a great class. It offers alternatives that don't rely on homogeny of variance and don't mandate equal size samples. If you have close to the same size sample groups, you're usually okay with the ANOVA adjustments. It does what are called type 1 or type 2 sum of squareds, but we're not going to worry too much about it. We're going to just say we're going to use type 3 sum of squared, and it is like doing regression or simultaneous testing. Is almost always recommended is type 3. So I think, did you guys notice when we did our AFEX ANOVA command before, it said type 3 ANOVA? It's the type of sum of squared. And this type 1, 2, and 3 comes from the authors of SAS. They call them 1, 2, and 3, and it just stuck, kind of like type 1 error and type 2 error. I mean, people like this should not be allowed to name things. Okay, all right, we ready to dive into the homework? Okay. Now, I'm excited that I saw that chapter 14, section B, number 6 question that you have to do by hand. or A number 6 is on the note. So I would rather that we dive into R because most of the problems in the homework are done with R. How do you guys feel about that? Okay, let's go into R. Okay. And all of the R ones, pretty much you have to write your results in APA. So we'll get 2 birds with 1 stone, 1 problem, and we'll do how to do it in R, post hoc test, getting our eta squareds. And let's see, okay. And how to write it up.
I'm stuck in doing the post hoc
The post hocs.
stuff.
Which
And I
one do
think
you want to start
that's 14C number 4, but if
The last one? That's a good one to start with. Or is it the last one?
is it number 5? I think it's number 5.
That's the last one. Okay, so 4. Okay.
14C number 5.
14, number 4.
No, where's it at? Ah! Oh, we start with C number 1 doing the post hoc stuff.
Okay, so let's start with number 1. C number 1.
Yeah, that's what's, I don't know if anybody else has something, but I'm struggling with those.
So if you're just opening this up and you haven't been working with it today, since you started R, make sure you run the run all chunks above button. So it will load your packages in and read the data set in and get it all ready to work. Okay. So let's see, okay, so I haven't touched, this is the skeleton, it hasn't been touched. So, and let me say this is something different so it doesn't, so it doesn't save over the skeleton. I'm known for doing that. Okay, so here we go. So it says, clean data set, line 426. So we're on line 426. So we're supposed to use college major and gender, those are our 2 categorical factors, as our independent variables, and perform a two-way ANOVA on the math quiz variable. So first thing has us doing here, the directions first ask us to do Levine's test. So what do we start typing? We always start with the name of the data set.
And then pipe that in.
Type it into car Levine test, Levine capital T test. And now we put our formula. The first thing that goes in our formula is our continuous interval ratio dependent variable, math quiz. And then we tilde away, and we usually put the 1 variable that we're doing grouping by. Here we're doing 2 variables allowing an interaction. So what do we want between our 2 variable names?
Asterisk.
Asterisk. So major F, asterisk, gender F. And then we have to do data equals dot.
And then do we need to do center equals mean on this one, or does it not matter?
Center equals mean.
And what does that remind us to do, or remind the test to do again?
If you don't, it tries to do center equals median.
Oh.
I don't know why. No, clean. Why didn't mine do it? Oh, maybe if I spelled clean. Right. There we go. Okay. So what does this Levine's test tell us?
Everything's good.
Everything's good.
We have homogeny of variance.
With the Levine's test, the null hypothesis is that there's no violations of homogeny of variance. And we are failing to reject, which is a good thing, because we can continue on with our ANOVA. Yay! Okay. So we're going to fit our two-way ANOVA. How are we going to do that? Again, we're going to start with the name of our data set. Now we're going to pipe it into...
Wait, don't we want to start with the variable first? Like the AOV math underscore two-way because we want to save it.
Oh, we're going to save it as something. Yeah, let's save it as this name. Yeah.
Just so we can reuse it.
Okay, has anyone noticed that I type really, really fast when it comes to the pipe and the assignment arrow?
Yeah.
Would you like to know a secret? There are secret keystrokes, and I try not to bombard you with too much information early on, but if you push Control, or for Mac users, Command, Shift, and the letter M at the same time, it will do space, percentage, greater than, percentage, space. Makes the pipe with the spaces. Now, if you have chubby fingers like me, or nails that get in the way of typing, if you accidentally push Control, Shift, N, that lives right next to M, it will make a new sheet, and you will be like, oh no, my work disappeared. No, it didn't disappear. Just, you know, get rid of that tab and you will be back to where you were. I swear I do that at least once a day.
That literally just happened to me and I panicked for just a second.
So there's that one. And then let's see, what's the other one? No, it's not that one. I have muscle memory. I just do them. Let's see. I can show you. You go to Help, and then Keyboard Shortcuts. There's all of these. I don't have all of these memorized. I only have a few that I use all the time. So let's see. Where is the assignment arrow? Does it have it on here? There's some of these are. Insert a pipe. There it is. Control, Shift, M. Right there. Insert assignment operator. Alt and the minus key. That's what it is. And then how do we get this off? Escape. Escape gets it off. Alt and the minus key will make your assignment arrow with the spaces around it. So those are some things to help you go. There, make that bigger. Okay, so we're going to save it as AOV Math 2, two-way. I put that. And we're going to start with the name of the data set, type it into AFEX AOV4. Now we need our formula. The formula is just like we did it in the Levine's test. Continuous dependent variable, tilde wave, both of the independent factors with an asterisk between them, except for what else do we have to tack on to the end?
The +1.
+1 observation per
line. Yeah.
Data equals dot. Now, if you're getting lazy and you don't want to move your mouse over to hit the play button, you can do Control Shift or Control Enter, and it will run the chunk. Control Enter runs the whole chunk. What did I get? I got a message. What is my message telling me? I got two parts to this message. First part's talking about what?
Well, we have missing data, which we knew that in math quiz.
Did we know about some missing data beforehand?
Mm-hmm.
Yeah, Laura, what was missing? Do you remember?
Weren't there fewer like stat quiz scores or
Math quiz. There's 15 people that didn't have the math quiz, and there's which lines they were on the data set, if you were curious. We already knew that, so I'm not worried. The second one, it says it's removing these cases from the analysis. Okay, so ANOVA is a listwise deletion. All it can do is listwise deletion. If anyone in your data set is missing any of those variables, they cannot be used. ANOVA requires complete data. So these 15 people that are missing math quiz, it doesn't matter that we know their major and gender. If we don't know their math quiz, we can't use them. So this should have a total sample size of 85, not 100, because of that. So that's what this first part of the message is telling you about. The second part is just telling you that major and gender are categorical variables, and it knows it, and it's going to use the contrast. That's perfect. That's okay. So that's fine. Now to get the basic output, we're going to do the name of the model, capital A Nova. Control Enter will get it out. Oh, wait, does it say? Oh, yeah, more. Oh, first we're supposed to do just its name. And then down here, we're supposed to add the $Anova. Read my directions. Now, both of these are type 3 Anova tests. This one says a digit 3. This one says a Roman numeral 3. I don't know why. The p-values are the same. Notice on this one, top one, it gives the p-values only to 3 decimal places. That's nice. This one gives our, what is this GES thing? What does that stand for?
Generalized eta squared.
Generalized or ordinary eta squared. Okay. What term should we look at first? Major, gender, or major by gender?
Major by gender.
The interaction. We look at it first. Is it significant? No. If it's not significant, then we move on and look at the main effects. Are the main effects significant? One of them is. Which one is significant? Major. How much does major influence math test score? Well, how would we interpret it with the GES, the generalized eta squared? This would say 12.6% of the variation in math scores is accounted for or explained by major alone. Major that they're majoring in, accounts for over 12.5% of the variation in math test score. Now this method of the output is nice because it gives you the generalized eta squared. That's nice. This one's nice because you get the sum of squareds if you want to do some other things. It also gives you p-values to more decimal places, f-values to more decimal places. So it, sometimes we want this way, first way, sometimes we want the second way, just depends. Okay, so what was the only variable that was significant? Major. So do we need to do an interaction contrast? No, because there is no significant interaction. Do we need to probe gender? No, because it's not significant. And even if it was significant, how many levels of gender do we have? Just male and female, and so any difference would have to be between male and female. But how many majors do we have? 5. So this F test tells us at least one major is different than at least one other major. How do we know which majors are different? Post hoc tests. And you do it the same way we did before. Now it says first we should do a summary table for math quiz for each major group. Okay, so if we're going to start with our data set, clean, and we're going to do columns in our table. We're going to dplyr group by one of our variables. Which variable are we going to group by? Major. And then we're going to make a table for the math quiz scores. Okay. Eyeballing it, which major has the highest math score on average? Economics, which one has the lowest?
Biology.
Biology. What about the other 3? Somewhere in between. Okay. Okay, so whoa, what's going on here? Oh, let's do Levine's test. Weren't we supposed to do Levine's test before? Yeah, we'll do it again. What's the difference here? We're going to do Levine's test for one group, and we're going to do, yeah, this is a little redundant, but let's do, yeah, let's get rid of that. That's redundant. We've already did Levine's test up here. Granted, it was for all the other groups, but it should still be the same. Not significant. Okay, so we are going to do a one-way ANOVA. Yeah, let's do it this way. So let's start with Eno, clean. And we're going to do a one-way ANOVA, AFX, package, NOV 4, and math quiz. Now, before when we did the two-way ANOVA, our formula, we put both variables. But what did we learn about both variables? There's no interaction. And in fact, gender doesn't do anything. So now we're going to fall back and only put major in. Make sure you add the one vertical bar sub num at the end of your formula. Did I spell something wrong?
Yes. Yeah, you found it. Okay.
Spelling, that's the first thing. Okay, so that does the ANOVA, but now we're going to pipe on EM means for the math, or for by major. And then you can do all possible pairs. Now, which adjustment method should we use?
Tukey.
Should we use Tukey? Why would we argue for using Tukey?
More than 3, right?
You have more than 3 groups, so that would say we should do Tukeys. But what else does Tukeys require?
Equal sample sizes.
Oh, Kimberly remembered.
Yes,
Equal
I learned that
group
the hard
sizes.
way.
Did our majors have equal group numbers? Not really. So I'm going to tell you to do Tukeys, but maybe we should have done Bonferroni. Definitely not Fisher's. So in this two-way ANOVA, the interaction was not significant. And in fact, so we looked at the main effects and only one of the main effects was significant. Since that variable had 5 levels, we followed it up by doing a one-way ANOVA on that one variable and did post hoc tests like we would have if we had done a one-way ANOVA to start with. I'm seeing some of these. Questions?
What does the EM means package? How do I know that that's what I'm trying to call? I mean, like, what does it stand for? Is it just
EM means stands for estimated marginal means, because we want to, now the margins are like on the edges, they're like the group averages. So margins are group averages. So we're comparing the group averages. And we use the estimated marginal means instead of the actual means because that's how it handles unbalanced sample sizes.
So it looks like biology and econ are the only significant
Yeah,
ones.
so if you look at all these p-values, there's only one set that's significantly different. we can only say that the highest major and the lowest major are different. We can't say anything about the ones in between.
Mhm. So on this problem in the assignment, it wants it in APA,
format.
which
Yeah.
makes it have hives. So
Have hives.
I don't know if anybody else has hives when it says that, but I do.
Yeah, are you guys worried about writing this up in APA? Okay,
It's just a lot.
there's a lot of stuff to
We
include
can get a
here.
ton of stuff.
Yeah, now, please don't worry about me judging you. This is practice for you. This is not judgment for me at all. But what we need to include everything that would allow someone who had your data set drop in their lap to be able to reproduce your results. So let's start out with the saying, what did we do? What are we looking at? What are our variables? What are the research questions? What did we start off with?
85 students.
We had the 85 math quiz. So 85 students, an undergraduate stats class was required to take a prereq math quiz. 80 of the 85, and now 85 we can write as a number because we don't have to write it out as EIGHT 85 in words because it's over 10. Of the 85 students with scores, because remember there's 15 that didn't, we also have self-reported gender and college major. So that we stated who's in our sample and what are the variables involved. Now we need to say what test we're going to run and why. What test did we run to start off with?
A two-way Anova, right?
A two-way, and we can call it a two-way, or what we can call it a blank by blank. What numbers would we put? Blank by blank. What are the numbers of factor levels? Major has 5 and gender has 2. So we'd call it a 2 by 5 or a 5 by 2. More often people put the smaller number first, but it doesn't really matter. 2 by 5 way, and no, and the first time we have to say analysis of variance, and then we can Anova. So the first time you do abbreviation, you have to like write the whole words out and then put in parentheses what you're going to call it for a shortcut. And then after that, we can just say capital ANOVA shortcut. The first. So what a two-way, 2 by 5 analysis of variance was conducted. Why?
To see if there were any, would we say interactions?
Yeah, we could say if conducted to investigate the effect, investigate potential effects of gender, major, and their interaction on math quiz. That's one way to write it. Or what if I was really concerned about major and gender was just like my side question? So it could conducted to investigate the potential, I could say, moderating effect of gender on major. Maybe it was, the ANOVA was conducted on quiz scores. So a two-way, 2x5 analysis of variance was conducted on quiz scores to investigate the potential moderating effect of gender on majors' role. So you can use the word moderator or moderating, or you can use the word interaction. Both are fine. Laura, you want to read it out loud and work it out? It's stressful the first few times. It really is.
Yeah. Well, I'm just going back through mine and like basically just rewording it to what you had.
Now, I don't want everyone's to be word for word like mine. I mean, this is not the only way. And this is, every time I do it, it's slightly different, you know. It just, a lot of it depends on where your focus is. And as a toy homework problem, you don't know where the focus is.
So I guess I'm just wondering where you were saying conducted on quiz scores to investigate the potential moderating effect. So do we introduce the variables as, or introduce our test as looking for effect or significance?
Or significance of the effect. It's up to you.
Okay.
Yeah, it's up to you. Usually, usually in your methods section, you have a subsection called participants, right?
Mm-hmm.
And then we usually have another one for another section for our measures. And then we have another section for our analysis. And we're kind of just like mushing it all together because we're not going into a lot of depth, right? So we need to say something about participants and the measures. And there's 85. So it's like these two are combined, because here I said we had 85 students. That usually would go in the participant section. But here we have about the other majors. And here we could say male or female, because it could have been other categories, right? And then here we could say, and 5 college majors, because, and 1 of 5 college majors. We need to somehow let the reader know that we had 2 genders and 5 majors. One way to do it in sentences. Another way is if you have a table. And so we could say the means, the summary statistics for the math quiz scores for all are provided in table 1. And then you put your means in a table for each of the majors and maybe each of the genders or some such way. So in a real journal article, we would have these different flushed out paragraphs. For this class, it's like you only have 1 or 2 sentences for all of those pages, because we're going brief, right? The whole goal is you need to know who, what, math test, gender, major, and how are we putting it together into a model. Now, that's all in the methods, the subsections of the methods. Then when you get down to the results, we usually start the results off with our, okay, so we might say, when you say you're going to do an Anova, you might say, usually we would say, and you don't have to do this, but usually we'd say assumptions, the assumption of homogeneity of variance, and I would show the abbreviation so I can abbreviate it from then on, test was investigated, oh, I already used that word, oh well, I'm going to be redundant, using Levine's test, significance level of 0.05 is used throughout unless otherwise stated. All analysis were performed in R 3. What are we in? Do you know how to find out? There, 4.0. R, wow, 4.0.0. Using the affects package. And usually we do italicize R. Have I shown you guys how to get the citations for R and any package? Have you guys ever noticed at the top of R when you start it the first time? It says right here, R is a collaborative project with many contributors. Type contributors for more information and citation on how to cite R or R packages. If you just do citation in your window with empty brackets, it tells you the citation to use for R. And if you do citation, but in there, quote, a package name, there's the citation for that package. And it gives it to you in an APA-like format, as well as a big tech format if you're doing that kind of method. Anyway, so R, when you do R, it's supposed to be R core team. Let's see, now we're on to 2020. This should be cited R core team. I don't expect this on the test or the homework, but, and then you don't have to cite every package you do, just the key ones that are like crucial, you couldn't do anything without. There we go. So again, this part, I don't expect you to put in your homework in your test, but this is what I would do in a real journal or a dissertation or a thesis. Make sure you say your significance level and how you did your analysis, which software, that's how I would, but again, not for here. So, and then the results, you start off like working backwards. So what are your assumptions? No violations of homogeny of variance were found. And we back ourselves up. Where was our Levine's test? Oh, here. Degrees of freedom are 9 and 75. And then the F value equals, I'm gonna grab this F value and that P value when I'm right there. F value we should do to how many decimal places? 2. P value we should do to 3, but don't put the 0 in front. Okay. So there's our assumption. Then what came next? Our two-way Anova. What did the Anova found?
That only major was significant. Oh, so we just say it that way. Huh.
Yeah. And right. Did that, it was, so F, it was, when we did that, it's 4 and 75. Here, I'm just gonna copy this, put it down here so I can see it while I'm typing. Ugh. Okay, not all that. You guys ever copy too much and you're like, go away? Okay, just that much. Yeah, so that's F, degrees of freedom 4 and 75 equal 2.69. What comes right after the F? Do I put my eta squared or my p-value? Usually the p-value. And then our eta squared, and I'm just going to do n2. Now, yeah, we'll leave it that way. We'll just do a generalized eta squared. How big is that? Is that big or is it tiny?
That, I think that's pretty close to that 14 cutoff.
14 is like the Cohen cutoff, so that's pretty big. Not huge, but it's pretty big. So found only, yeah.
So do we keep eta squared to 3 decimals too then?
You can do 2 or 3.
Okay.
Yeah, either's fine. In fact, 2 would probably be better. Yeah. Then we can say, then what do we do for follow-up? A follow-up one-way ANOVA with pairwise post-hoc tests established that the biology majors scored much lower than econ. Scored, well, we can say scored 2, yeah, scored.
Do you want to say significantly lower, or are we not stating? Yeah. Okay.
And for that one, we would need the t-test. There, it's right there. So we gotta go up here. So what's the t? How much lower did they score? On average, 11.16. So you couldn't say, usually we do that a D bar, the capital D with a bar on the top of it, the difference was 11.16, and we usually make it positive because it's only order that makes it negative. And the T ratio has how many degrees of freedom? 80. And it's equal to 2. If I'm going to go 2 decimal places, 2.90, 2.90, and the p-value is 0.038. Now, what have I told them everything I did? Is there anything I need to tell them? There's one more thing I need to tell them. I was just, not if, there is. What thing have I not told them that they would need to know that I did in order to reproduce my exact numbers?
We've got to tell them it was Tukey's somehow.
Yeah, we used Tukey's. Have we told them that?
Mm-hmm.
No. So
like,
follow up one-way ANOVA with pairwise post-hoc tests utilizing Tukey's HSD adjustment for multiple comparisons. So this is how I would write it up for kind of for a journal, but for class, it doesn't look as bad if you do it like that. And even if you want to make it one paragraph. Who are your participants? What did you measure on them? Why did you do it? What are you trying to look at? How are you going to investigate it? What method are you using? Are there any assumptions? Are there any follow-up tests? Any multiple corrections? And you really need to convey what was significant. And you can't just say that biology and econ majors were different. You need to say which one was higher and which one was lower. So it's important this word lower in there, not just that I say that there was significantly different. Okay, the only thing we haven't done are the interaction contrasts. I really wanted to show you one of those. Okay. Oh, for the, oh yeah, I did. I think I combined those. Yeah. Okay. Let's see. If anyone needs to go, no judgment on my part. Go ahead and go. I'm going to stay on even if nobody else does, and I'm going to go through the next question so that you guys can have a reference to look back for interaction contrast, since I didn't show you the syntax directly for it. Okay. So again, if you have prior commitments and you need to go, you're fine. Okay, so this is number 4, part A. So we're looking at the phobia. We need to go back to that phobia grouping variable. We used to have a phobia grouping variable back in chapter 12, and we're going to use that with the gender variable to do a math quiz ANOVA. So we're still going to do, oh, the phobia grouping variable I put in here. So if you go up to the top where there was Eno's clean, here's the phobia grouping variable. I already put it here. Right here. I said if phobia is less than 3, 3 or 4, or 5 or greater. So I've already created the phobia group variable in here for you. So it exists in here. So here I can do a table. Now this table, here's your cell averages, basically what I did. This isn't the easiest thing to get out, the cell averages, but let's go ahead and make a plot. We haven't done one of these plots directly. So again, when we make a plot or fit a model or test an assumption, we always start with the data set's name. Okay, so start with the data set name. Now we're gonna, to make a plot, what do we use? ggplot. The first thing we have to give a ggplot is aesthetics. Now we have to choose an X variable and a Y variable. The Y variable is always going to be your dependent variable, the continuous interval ratio score we're comparing the average of. And here we're comparing math quiz scores. So math quiz is our Y variable. Now, as far as our choice for our X variable, we can either choose gender or we can choose phobia group. It's always better to choose the variable that, if you have to choose between them, the one that has more levels for the x-axis or the one that's more ordinal for the x-axis. So out of the two, gender or phobia group, which one should we put for the x-axis?
Probably phobia group. So
I'm going to choose phobia group. Yeah.
Right. Okay.
Now, if we have another variable, it's a good idea to choose that other variable. You can make the shapes of the points different by the other variable. So I can make shapes by gender. You can also do color by gender. You could do both, which helps if you photocopy it. Color is always helpful if you can view it. If you're colorblind or photocopying, it doesn't always help. So it's good to be redundant there. And then just add on stat summary to make those points with the little whiskers. Now, for a long time, I couldn't figure out how to join the dots with the line, but I finally figured it out a couple months ago. You have, if you want to do that, which it doesn't ask you to, you have to do another stat summary, and you say fun equals mean, geom equals line. I think we have to quote line and mean. Ah.
I'm thinking you did give us the code for that. I think it's fun.y or something.
Fun.y, but they got rid of it.
And then mean is not in quotes, I don't think.
It can or it can't be. I know what it is. I know it's not doing it because of those missing cases. We need to filter complete cases. And again, this is not mandatory that you do this step for the homework. I'm just not spelling very well today. Oh, look, there's, oh, that's 11. I don't want to go to 11. Complete cases. Okay, yeah. So I had to, oh, it's still not doing it. I think that you're right that it had, no? Did I do it over on this one? I did it on this one. How did I do it? Fun. Right there. Fun dot mean, fun equals mean, geom equals line. Oh, I remember. You have to go up here and say group equals, you have to have the group specified in the aesthetics. That's what it is. I think I can take this off. Yeah, that's what it was. You have to have group in your aesthetics. Now I could also do line type equals gender F if I wanted to be super redundant. But I don't like that because it makes the error bars dotted. So I usually leave that off. Okay, so let's see. What does it look like in the low phobia group? Females are higher than males, but there's overlap. What about in the moderate phobia group? Females are higher than males, maybe a little bit more spread out, but still overlapping. What about in the high phobia group? Smaller, they're tighter together, but females still a little bit higher. So do we have crossing? No, we don't have crossing, but are they lines perfectly parallel? No, so we could have an interaction, but they might be close enough to parallel and not significantly different. So, excuse me, we might have an interaction, we might not. We need to run the test. Okay, so Levine's test. What do we start with? Clean, the name of the data set. Pipe it into car package Levine test. And math quiz is our continuous dependent variable. What do we put on the other side of the tilde wave this time?
Do gender F. Bob group.
Gender F asterisk phobe group. Data equals dot and center equals mean. Yeah. So in Levine's test, we just have, after our asterisks, after our tilde wave, we have our two factor variables separated with asterisks. So Levine test tells us what?
P-value is not significant. So
We have no violation, no evidence of violations of homogeny of variance. Okay, so we're going to do our two-way test. So starts much the same, except we're going to do affix AOV4. And on the end of the formula, we have to add on the 1 per sub num in parentheses. And we're supposed to save this as a name, right? That'd be a long name. So what do we find in this one? Is the interaction significant? Nope. Is phobia group significant? Yes. Is gender significant? No. So we only have one significant main effect.
It's interesting that gender's not, when it was high for all three, females were all three higher than males, but I mean, I guess it's because of the small group size, maybe?
Yeah, but also look at this. The female is a little bit higher than male, but what do you notice about those standard error bars?
Oh yeah, they're overlapping.
They're completely overlapping. So because of that, there's no significant difference between men and women. But it says there is a phobia group difference. So up here, phobia is higher, and down here, phobia is lower. See, we got higher, and then in moderate, lower. Now, does it go back up or does it stay down about the same? That's how will we tell the difference? Phobia group has how many levels? 3. So when the F-test says phobia has an effect, we need to do follow-up tests to see which of the 3 groups differ from which other 3 groups. So it's, now this is another way to do post hoc tests. So it says request all pairwise post hoc on EM means. So you can take your two-way model, and this is the way I prefer to do post hoc test, is to do EM means right on the two-way model. And we're doing it for which variable? Phob group. Now I'm going to stop there. I'm not going to do the pairs yet. Watch what happens when I run this. What do I get? I get a line for each phobia group. And what does it say in red at the top? It gives you a warning. It says results may be misleading due to involvement in an interaction. Because should we look at phobia group by itself? What's the caveat? Only if this interaction was non-significant. So this little red warning message note is don't do just phobia group by itself unless you've made sure that the interaction is non-significant first. Okay, because it says you're averaging over both levels of gender. So the EM means gives one line for each phobia group. Now we want to do all pairwise tests between those groups with adjust equaling none. Why do we do adjust equals none? Because it will, that's how you do Fisher's LSD. And with 3 groups, we should do Fisher's LSD. Okay, do you guys want to go over APA results? There's another way languaging we can do here. Instead of the way we wrote it before, we can write it a different way. We can say math quiz was subjected to an Anova. So we could say the math quiz scores for 85 intro stats students were, I guess it's plural, subjected to a what by what ANOVA. What were our two variables? What were our two variables? Phobia group, and it had how many levels?
3.
3. And gender, it had
2.
2. So a 2 by 3. Where am I typing? There we go. 2 by 3. And now analysis of variance. So we got 85 students, math quiz. Now we got, what do we also have to add in here?
The
I've
2.
got math quiz, 85 students, analysis of variance.
We have to say something about phobia group and gender.
Yeah, yeah. With phobia group, low, medium, high, and gender, male, female, as the two independent factors. So that's another way to write one sentence that has how many students, what's the dependent variable, what are the independent variables, how many levels do they have, and that you're doing a two-way ANOVA, all in one sentence. This comes from trying to publish papers with very small word limits. So that says what our method's going to be. Now we need to say, so that's everything we need for methods basically. What is, except for what does it leave out?
Assumptions?
Assumptions. Yeah, so we need to write something about our assumption. Yeah, I'm going to grab this. So Levine's test found no violations of the assumption of homogeneity of variance. Oh. Seven, 3.138. Is there an effect size for Levine's test? No, Levine's test is one that you don't need to worry about putting an effect size, especially when the Levine's test says there's no difference. Not significant. There's no reason for an effect size there. Okay. What comes next? What do we need to go with next?
Then we look at the results.
Then we look at the ANOVA results.
Mm-hmm.
That's the only thing significant. So, indeed. No. So we should say gender or phobia group did have a main effect, and main effect is a term you can use, and it's degrees of freedom. How do you do degrees of freedom here? Oh, it's up here, phobia group, there we go. 2 and 79. Be careful, it's easy to get the MMSE instead of the F statistic. The p-value and the eta squared value. However, gender had no, however, there was not evidence that gender had a main effect for gender. 1 in 79. Should we put an eta squared with gender? Up to you. I'm gonna make the
We
eta.
don't have to. I
No.
was wondering, do we want to talk about that there was no significance in the interaction?
Yeah, so this is how I was gonna phrase it. Phobia group had a main effect. However, there was no evidence that gender had a main effect. And I'm just finishing this. And it's less than 0.01, nor had a moderating effect on phobia. Effect over phobia. So usually we interpret it first, but if it's not significant, we talk about it last. It's not a hard and fast rule, but it tends to flow maybe a little bit better if you talk about it that way.
So why is the degrees of freedom for Levine's is 5?
Because there are 6 total combination groups.
Okay. Okay.
Yep, that's a good call. The degrees of freedom.
And then it's 3 by 2, so it's 1 less for the other. Okay.
And we didn't talk about the rules for finding degrees of freedom for Levine's test.
Sarah, do you want this typed up in R?
No. I'm just doing it so it's on my screen.
Okay, got it.
If you want to type it in R because it's right there and then you can just copy it and paste it into Canvas, that works.
Okay.
But you're not required to know. I'm just doing it because it was handy.
Yeah, no, it's great.
I didn't want to open Word and then have to flip back and forth.
Right, right.
So, okay, so that gets me through the Anova results. So the Anova results tell me there's something going on with phobia. At least one of the phobia groups are different, but since there's 3 phobia groups, we have to do
We did Fisher's.
pairwise post hoc test with Fisher's LSD adjustment for multiple comparisons. And what do we find here? Low versus moderate? Different. Low versus high? Different. Moderate versus high? Not different. So it helps to go back and look at the plot. So this low is different than both moderate and high, but moderate and high are different than each other. So we could say that low phobia scored substantially better than the moderate and the high phobia groups. So we say, look at this sentence is halfway wrote for us. Pairwise post hoc comparisons using Fisher's LSD adjustment for multiple comparisons found that students who rated themselves as having low math phobia scores less than 3. That's what it meant, right? Had higher math quiz scores. And you can actually put the means in here, scores, than those in the medium phobia, which was rated 4 or was it 3 or 4? 4. And that was a T there that was 79 degrees of freedom. Low versus moderate. So low phobia had higher scores than the medium phobia, and high phobia rated 5 or more. And then you might want to say, so far I've ticked all 3 of those F statistics off, right? And now I've gotten 2. Now I need to get the last T statistic on there. No evidence was found for a difference in math quiz scores between those students who rated themselves as moderate or high on math phobia. Now, again, the T statistics, we generally just report them as positive values because it's just the order that you subtracted them in. Let's see, where are my other typos? I'm sure there's plenty. There.
So how do we remember when to put like group degrees of freedom by total participant degrees of freedom?
The good news is degrees of freedom will always be listed on the output.
Okay.
So you always need a degrees of freedom to go with the t-test. You always need 1 degree of freedom to go with the t-test and 2 degrees of freedom to go with an f-test.
Okay.
Is that what you meant?
Yeah.
Yeah. The formulas are on the formula sheet, but the output will always give them to you.
Okay.
Now there's a lot of things to include here. What's the main takeaway? What makes a difference on math quiz scores? What's the only thing that we were able to show for sure made a difference on math quiz scores?
Low math phobia,
How they rated themselves for the low.
medium.
High phobia, low phobia did better than moderate or high phobia. That's the only thing we can establish. Gender, we can't establish any gender differences. So it's like you have 1 level here and 1 level there. So even though there are 6 dots on our plot, there's really only 2 main averages. Because this is 1 level, and these 4 dots are like another level.
Okay.
Okay, the next part has us repeat it without the moderating group. Oh, I don't have you doing interaction. I don't have you doing interaction contrast. Well, looky there. How lucky are you guys?
So this, on the homework, it asks, what type of interaction do you see?
What type of interaction do you see?
And is that just,
Is it an explain box?
no, it's just a multiple choice. Okay.
Options are,
Repeat part A, except post hoc after deleting the moderate phobia group.
okay, so let's delete that. And we're supposed to make another plot. So let's make are we supposed to do another plot?
That's what
No,
it says. on the
practice.
homework.
Does it? Oh, let's make another plot. It didn't, there's not a spot for it. Can we add a spot? Yeah. The way you add a chunk, you can either type it or up here in the corner, in the upper right-hand corner by where we make that little outline where it says insert, and then select R for our language. So we can go and let's go get this plot. And let's throw in this filter line. Oh, I need a pipe on the end of it to connect it to everything else.
Sorry, Sarah, can you scroll up just a minute?
Yeah, let me, I blew up my screen and now it's zoomed. Come on. Can I zoom out?
Because mine is showing that there is a place for this. Are you guys seeing that? 14C4B, repeat without the moderate group.
Yeah, it had, but this is where you're supposed to put the Two Way Anova.
Oh, okay.
It doesn't have, mine doesn't have a place for the plot. Does yours?
No.
There we go. Okay. Oh, that might have gone too far. There. It's tiny. Can you guys read that at all?
So we don't need that line with the complete cases. You don't think that's not helpful? Okay, cool.
Yeah. The problem was I didn't before it wouldn't work because I didn't have the group in there.
The group. Okay.
Yeah, that's what had to be in there. Okay, so this is what we're supposed to look at. So we could have just covered up the middle and pretended before, but we can actually make this plot and say, what kind of interaction do you see?
Okay. Sorry, I'm trying to figure out where you put it in, just right under the instructions. The
Yeah,
textbook.
I put it in right after the textbook question before the directions. It doesn't matter.
Okay.
Is that looking for like ordinal?
Is it ordinal, disordinal? No,
It's not disordinal. I think it'd have to be ordinal.
If anything, it's ordinal, but what do you notice about the standard error bars?
You got the good overlapping.
They're way overlapping. And when they're overlapping, what does it mean? It means they're both basically the same point. So over here, we have basically the same point. And over here, we have basically the same point. Because the pink and the green or teal, coral and teal, whatever colors these are, the error bars, the standard error bars are overlapping. So that tells us basically those points are the same. And on the other side, we have the same thing. So even though we see a gap between the lines that's unequal, they're essentially the same line within a standard error. So what type of interaction would you call that? What, Kelly?
Well, I said there's no interaction.
Yay! Trick question, I guess. I didn't make these questions up. They're from the book. I'm sorry. I take no credit or shame.
On the low side, I'm seeing the error bars, both of them, I'm just not seeing the error bars on the high side.
Because they get covered up. You can do this. I'm going to do this and then I'll tell you what I did after you look at it. It'll make sense in a second. Okay, so what I've done here is I've taken the positions of the point and I've dodged them off so they weren't totally overlapping, because they were overlapping like this, and I dodged them so they're just separated a little bit. But in the way you do that in R, you say position equals position dodge, and then width. The width between low and high is 1, and so I didn't want them to be all the way over. I just wanted them 0.2, just a little bit off of each other, so that you didn't see, because before when they were overlapping, you couldn't see them. The error bars for one color were completely covered up with the other color. And it puts the error bars on first, and then it does the points, and then it does the lines. So this helps uncover, so they're not covering each other up, and you can see how much they're overlapping. The key is if you do it to one stat summary, you have to do it to the other stat summary.
So I'm seeing there's significant overlap on the high side. There's a little bit of overlap on the low side. So does that still mean no interaction?
It looks like no interaction. If anything, they would be ordinal, not disordinal, right? Because on the high phobia, they're almost exactly the same. They're really overlapping almost completely. Now, look at the standard errors. Are all the standard error whiskers the same length?
No.
They're not, because we don't have perfect homogeny of variance. We're close enough that Levine's test says, go ahead, you're good enough, but it's not perfect. But it's same-ish.
So we would consider this as no interaction, or like, because spreading seems like it would be getting further apart, or?
Yeah, you see some ordinal interaction, but it's suspicious that it might be no interaction, because these are completely overlapping in the high phobia group, and in the low phobia group, there's a good degree of overlapping.
Mm-hmm.
If they overlap at all with the whiskers being one standard error, they're almost always non-significant difference. Because remember, this is not a 95% confidence interval. This is just plus or minus one standard error for the mean.
Right.
So it's highly likely that these are basically going to be considered the same. But it's not disordinal. They're not crossing.
Okay. I'm also just curious as to why mine didn't let me plot.
Do you want to share yours?
Sure. Can I real quick? Yeah. Okay. Let's see. Yeah. Sorry.
Oh, that's okay.
All over. Okay. So is it an exclamation point here?
Yeah. Run that much. Let's see. Try running it all right now. Oh, I think you have an extra closed parentheses after moderate.
Is that it? Okay.
Yay!
Awesome.
Yep.
Okay.
Isn't Zoom nice? We can just say, oh, there it is. And then life can go on and you don't just hit your head against the computer all day long, right? Okay, because it's usually something like that. Okay, so let's actually do the two-way ANOVA to see if that's a significant interaction or not. Oh, and I could have, oh, I'm supposed to save this as something. Oh, yeah. Okay, we'll save it. Oh, I was supposed to do, what did I do wrong? Someone catch what I did wrong?
No, I'm just trying to catch up.
So I'm naming it this name that it told me to name it, AOV math phobe to gender. So I started with my data set. I piped the filter to get rid of the moderate group. And I did my Anova math quiz by phobia group, 1 observation per subject, data equals dot. Kelly, Melissa, can you guys see what I did wrong? It's something that's missing.
I'm just trying to.
The pipe? No.
It ran, it's just wrong. I went to answer the question, I'm like, oh, I can't answer that because I did it wrong. What kind of Anova did I do?
You do like a simple, like a one-way?
I did a one-way. What are we supposed to be doing?
2.
A two-way. What did I leave out?
I don't remember.
Check my formula. I have math quiz by phobia group.
Oh, the multiplication?
What about gender?
Yeah.
I forgot my gender. Because I went to look at my results, I'm like, I don't have an interaction in my model because I only had 1 variable. So you can't have an interaction with only 1 variable. You got to have 2 variables to get an interaction. Is the interaction significant?
It looks like there's one, the interaction isn't significant, but the phobia gender
Or just
is
the phobia group.
that main
Is
effect.
phobia or gender or both significant? Check out gender.
No.
Looks like phobia group is significant.
Just phobia group is significant. So if we look up here, so is there an interaction? The p-value says no interaction. So even though the lines are not perfectly parallel, they're basically parallel-ish. So there is a little bit of spreading, but it's pretty much like they're the same.
Yeah, looking at it, I would have thought definitely.
Yeah, if you look at just the lines, but if you remember to look at those error bars
Yeah.
too. That's why it's important to have those up there. Okay, so now we've established that the only thing that's significant here is phobia group. Do we need to do a follow-up test on phobia group this time?
No.
No, because
There's no interaction?
that's not why.
Or
That's true, that's not why. Why don't we need a follow-up test on phobia group now?
Oh,
Because there's only 2 groups.
Because there's only 2 groups, because we got rid of the moderate group. And if you only have 2 groups, the only way they're different is if those 2 are different.
got it.
That's the Canvas asks that, right?
So yeah, it does. So, okay, because Fisher's is what we use with 2. The 3 groups. And Tukey's is with 2?
4 or more that are the same size. And Bonferroni you can always use, even though it might be a little severe.
Okay, so when we have 2 groups left, or when we eliminate our 3rd group, then
2 groups, you don't need to do a follow-up test because there's only 1 pair. The only way for that the variable to be significant is if the 1 pair has a difference.
Okay.
If you have 3, you gotta do Fishers. If you have 4, you do Tukey's, as long as they're 4 or more, they're roughly the same size.
Hypothetically speaking, if gender had an option for other, then would we need a follow-up?
Only if the F test is significant first. Here, the F test was not significant, so no matter how many groups there are, we don't have to do a follow-up.
Okay. Awesome.
How many steps are there? A lot. A lot. Okay, are we ready for 5? This is the last one. Okay. So here we're looking at the phobia group variable again, but we're looking at coffee drinkers as our second factor. And we're comparing what? What's our dependent variable? It's our
Post heart rate test.
heart rate. Do you think phobia affects heart rate? How math
Yeah.
phobic you are? I'm taking a pop quiz, surprise pop quiz. What about if you drink coffee? Could that hypothetically have an effect on heart rate? Yeah. So we're going to see, do they each have an effect, and do they moderate or affect, have a combined either enhancing or detracting effect, suppressing effect.
Mm-hmm.
So first thing we're going to do is make a plot. So I'm going to go back and grab this plot that we did up here that I had, the position dodge one, because that's fancy. But I don't need to remove the middle phobia group. Now, we're still using phobia group, so that's all great, but we're not going to do gender. Instead of gender, we're doing what's the second variable?
Coffee.
Coffee. So all my gender Fs I'm going to replace with coffee F. Whoa, check out that one. Have we seen a plot this fun?
Mhm.
What kind of interaction would this be called? I don't think I asked you, but. Ordinal or disordinal?
Disordinal.
Disordinal because
It crosses.
they cross. Yeah, the order swaps. Here, the coffee drinkers are higher, coffee drinkers are lower, coffee drinkers are higher. So we see a disordinal pattern, but do you think it's statistically significant?
Yeah, I think it probably is.
Yeah, we'll see. Okay, so the thing we're gonna do is check Levine's test.
Can you scroll up just a little bit so I can see the bottom of yours? How to make, okay.
So the position equals position dodge, width equals 0.2.
Yeah.
Totally optional. That's
Well, I
nice.
did that and it came out really funky. Or like it just came out really boring. And so I'm like, why did that happen? Okay. Fun equals mean, GM equals line, and then the position again. Okay, sorry.
I think I'm gonna have to, this video, I should have stopped it and started it so it was separate. It's gonna crash when I try to upload it. Why do I think about these things too late? Okay. Levine's test. Huh. How do I write my formula? What do I start with?
Oh, you already have that.
The tilde thing,
What comes before the tilde?
the dependent variable,
The dependent variable, which is
the heart rate.
heart rate.
Post.
Oh, this isn't the right plot then. What did I plot on my y-axis? Math quiz. That's
Okay.
not right.
This is why mine looks so different.
It's HR post. Is that what yours looks like?
Well, yeah, much more like that.
Yay.
For the first time, probably for the first and last time, I I was not the one who erred.
No. I was, see, copy and paste. Copy and paste got me in trouble. I copied it and didn't change everything.
Yeah, that's definitely more like what I got.
The post-quiz heart rate. HR post, tilde wave, copy, F, gotta spell that wrong, right? Asterisk, phobe, group, data equals dot, and center equals mean. That really bugs me that that's not the default.
Man, who knew coffee could affect math quizzes, though? From that last.
It wasn't, but the error bars were overlapping, so my guess is it would be non-significant.
True. That was so interesting, though. They should have kept that problem.
They should have. Seeing how it's made up data anyway.
Darn it.
Okay, so does the HOV test give us cause for concern? Whew, glad. Okay, so let's do the Anova. You guys have got to be like brain fried.
2 more weeks. That's all I just tell myself.
1.5.
True.
You guys are just rock stars for making it this far. I mean, this is insanity.
You are a rock star, Sarah. Getting us through this.
Yeah, I appreciate it.
Do you think that you've gained something by being totally immersed in it like every day?
Yes.
I think there is something that's gained from it. No, I don't know that I would choose it if I were you, but you know, there is a little trade-off.
It helps me a ton because I have to like totally focus. So trying to juggle other classes is not helpful.
What did I do wrong? Oh, I have a space in subnum. Spelling, it gets me every time.
Oh, crap. What did I do wrong?
Is it a minus or a tilde wave between HR
Tilde.
post? Oh, okay.
Maybe that's a little bit bigger, maybe not so tiny. HR post, tilde wave, coffee F, asterisk, phobe group. Talk like we're in a comic book.
Okay.
So Melissa, what does this tell us? Oh,
We-
I'm supposed to save it as a name.
Both of the main effects are significant, but the interaction is not.
Yes, that is correct. Both of the main effects are significant, highly statistically significant, but the interaction is not. So coffee does affect heart rate, and phobia does affect heart rate, but they don't moderate each other. Which has a bigger effect size?
The phobia group.
Phobia group accounts for double the variation that coffee drinking does. Now, which of these two variables needs a follow-up test?
How many groups are there in each of them?
That's a good question. How many groups are in coffee? Here.
Well, phobia had 3.
Uh-huh.
And in the last one we took out 1. Is that still applied here?
We've left all 3 phobia groups in here.
Then we would want to look at phobia.
We would want to do a follow-up test on phobia because it has 3 groups. What about coffee?
Coffee, if it's just not a regular coffee drinker and regularly, then we don't need it to follow up.
No. So we can say regular coffee drinkers have higher heart rates than non-coffee drinkers of all phobia groups.
Mhm.
Now we need to do the follow-up on phobia groups. So we can take our model and we pipe on EM means by phobe group. And what's it going to tell us? Careful, caution, you have a two-way model that might have an interaction. Make sure it's not significant before you look at this because you only have one variable here. And what are we going to do? What kind of follow-up test?
Fisher.
Yeah, Fisher's, because we have 3 groups. Yep. So we do pairs to do pairwise. And how do we do Fisher's?
Just equals none.
None. Now let's see. Is low different than moderate?
Yes.
Yes. Is low different than high?
Yes.
Yes. Is moderate different than high?
No.
No. So these lines are crossing, changing gaps, or essentially parallel.
Changing at first, and then they become parallel.
They look like they're changing, but what does this ANOVA tell us? If there's no interaction, they're essentially parallel, with a little wiggle room.
Mm-hmm.
I mean, they're not perfectly parallel, but they're parallel-ish. That gap is not exactly the same size, but it's approximately the same size all along the lines. Doesn't mean it's straight. They're
Right. Okay, so just the interaction. There's no interaction.
no interactions means they're basically parallel. They're not railroad. It goes up and then it's flat, basically.
But there is a significant difference in the low to moderate and low to high.
Yeah.
Okay.
So if I looked at this plot, even though it looks like the gap here is smaller and bigger here,
Mm-hmm.
because there was no interaction, because the interaction was not significant,
Mm-hmm.
that means the lines are basically parallel. So the gap is essentially the same all the way along them. Now, we saw coffee was significant, and we can see by our picture that the coffee drinkers have higher than the non-coffee drinkers. But then when we did for phobia group, it was significant, main effect. And when we checked it, it showed us that low phobia group had a lower heart rate than moderate and high, which were higher. So if I was, even though the data is kind of more complex, let's see if there's something. Okay. It's essentially saying, let me erase this all. Yeah, I'm gonna put this over here. That the blue line is essentially going like this. It's essentially flat here because we saw moderate and high are essentially the same. So this is essentially equal. But here we have a gap, right? Because low is different than moderate and high.
Mm-hmm.
But so in this group, it would be down here, it would be essentially the same, just shifted straight down. Now, there is some wiggle room in the data, but the only evidence we have is that there is a difference between low phobia and the moderate and high group. There's a difference between coffee and non-coffee drinkers. But since there was no significance in the interaction, the lines are essentially parallel. I like to think about it on the plot. I really have to use the plot. Okay, you guys need a break. You need to go like get some chocolate and go walk around and get some fresh air. Definitely. So I'll adjust the due dates as soon as we log off. I'll adjust the due dates and I will put up announcement reminding, and then tomorrow we'll have office hours at 10:30 in the morning and 7 in the evening.
And Sarah, you said the test would be like, for these three, would be like a couple of multiple choice questions and then analysis for one. So like one of these write-ups for just one.
For one. Yeah, I don't want to kill you guys.
We appreciate that.
Okay, so in limit, Kimberly, you said on 14A number 6D, it says, what are the limitations of an ANOVA? So on that one, that was one where we have categorized people according to whether or not they are an exerciser or a non-exerciser, and whether or not they're following a vegetarian diet or not. What type of study is that?
Observational.
Observational study, because we didn't randomize the diet and we didn't randomize the exercisers. That was just an observed self-selected or whatever. It was just, we observed it. It's an observational study. So even if we say things are associated, we cannot say that they're causation. So here we might be able to say that coffee drinkers had a higher heart rate, but can we say coffee drinking caused the heart rate to be higher? No, not unless we randomized it. And so we can say coffee drinking is associated with higher heart rate, but maybe it's people that are more anxious and that's why they're drinking the coffee and they also have higher heart rates. Or, you know, I mean, it makes sense. We just can't state it as a causal relationship. We can only state it as an association because we observed, we didn't randomize.
All right, thank you. That's perfect.
Okay, really, you guys, go take a break.
Thank you, Sarah. I really appreciate your help.
Best debugger is a good night's sleep, and sometimes the best study strategy is a good night's sleep. So go find something you enjoy to do for at least an hour before you even think about this, at least.
Thanks, Sarah.
Yay, bye.
Thanks, Sarah.